Thank you, guys. So let's start. It's my pleasure to welcome you at System Boot and Security micro-conference. I will be driving this micro-conference together with Matthew Garrett, who agreed to take minutes, and thank you, Matthew, and Joel Stanley. Some information about micro-conference. We have 2 blocks of sessions. First one will be devoted to OpenBMC, UEFI, SGX, and some stuff about DRTM. Then we will have a break between 4:30 and 5, and there will be a whole block devoted to the TPM. Some information for the speakers. All slots are 20 minutes long. So we have quite tight schedule. Please start as early as possible and finish on time. Additionally, we have throwable microphones. Please do not start speaking without them, because simply nobody will hear you, especially on the recording. I think that's it. We can start, and the first presentation will be done by Joel about OpenBMC secure and trusted boot. Thank you.
Thanks very much, Daniel. Hi everyone. I'm Joel. I work at IBM, the Linux Technology Center. I spend all my time, or most of my time, working on the A-Speed BMC. Who's not a BMC is? All right, not many. Who doesn't know what a BMC is? Who doesn't want to know, raise their hands. Thank you. So a BMC is a baseboard management controller. It's typically an ARM microcontroller, or ARM Linux system these days, that sits on the motherboard of your server and provides things like fan control and remote access. So when your system crashes and you need to get a serial console, you log into this BMC thing and can talk to it. Until a couple of years ago, it was generally something that your system manufacturer bought from some BIOS vendor somewhere, and it had all the qualities of that kind of Linux stack. So we threw it all out and started from scratch. So at IBM, I did the kernel along with my team. So that was doing an upstream ARM port from scratch for the A-Speed 2400 and 2500, and then we had a team doing user space. There was also a project started at Facebook at a similar time. They also got OpenBMC. And in January last year, we kind of all got together and shook hands and incorporated under the Linux Foundation as a Linux Foundation project. And now we've got all the cloud companies, all the people making servers, all kind of jumping on board and doing this OpenBMC thing. And I was just over at the Open Source Firmware Conference in California last week, and we had a whole heap of kind of software companies doing value add on top of OpenBMC as well. So they take the OpenBMC stack and put their own web GUI on it and all this kind of gear. So that's a bit about OpenBMC and what it is. And so yeah, I work on the kernel, and we were starting to do design of the next generation systems and started talking about the lack of any kind of secure or any kind of knowledge about what boots on it when you run your BMC. At the moment, it just grabs pages from Flash and off it goes. So we have a pretty typical embedded ARM boot sequence. We have U-boot on some kind of NOR flash. It starts executing from Flash. It trains the SDRAM. And once that's trained, it relocates itself into SDRAM and loads some kind of kernel from somewhere. In this case, we wrap the kernel in a fit image. That's a device tree with a bunch of blobs in it. The blob being your kernel, your actual boot device tree, and often an init RAMFS, but not necessarily. And from there, we load the rest of the user space from a squashfs petition. And that's kind of how most of the OpenBMC systems work. And so in that process, there's no real verification. I mean, the fit has some SHA signatures to make sure that what you're loading isn't corrupted, but it's not checking that against any kind of expected values. So no secure or trusted boot. So the new hardware has some hardware root of trust. This is the A-Speed 2600. I've spent the last couple of months doing bring up of that, and 5.4 will be able to boot it out of the box, which is kind of cool. And if you grab QEMU Master, you'll be able to boot, very soon you'll be able to boot the A-Speed in QEMU as well. So we've done a hope of work there to make it easy to write kernel drivers, and also for the user space team to do their testing, getting upstream code support. So the new hardware's got this hardware root of trust. You can put some keys in the one-time programmable memory, and then when the system boots, it will, there's a boot ROM inside the system on chip. It'll load a chunk from your boot device, whether that's eMMC or SPI-NOR, and do some verification of it, and then execute it. So that's the hardware design. So this was an initial design for how we were going to do secure boot with this. You could put the keys in the BMC, put the UBoot SPL, that's the 32K blob that gets loaded initially. The UBoot SPL verifies UBoot verifies the fit, Linux then starts, and from there on it's a user space problem. I'm the kernel and UBoot guy. But the big downside of this is that if you are the kind of company that's making machines that you're selling to someone else, so someone else can't replace their code. And that was something I raised as a problem. With the hardware solution they have, it's not really clear how you fix it. If you leave the key slots open, someone can put, a malicious actor can put their keys in there and sign their firmware. So it wasn't really clear what to do. Spoke to the guys at research, and they came up with a trusted boot solution. So it means you don't get secure boot from the first instruction all the way through to your Linux kernel. You have secure boot for the first stage bootloader, it's the UBoot SPL, and then that loads any old UBoot that's in Flash, and that UBoot then can do secure boot with keys that are in an EEPROM. And the way you verify this is all secure is you are recording each of the boot stages into the TPM that's now attached to the system. Just as a bit of a disclaimer, I'm the kernel guy, I'm not the security guy. It's all new to me. This is why I want to do this presentation today. So if you are the experts, please grab the throw box and tell me how wrong I am. And so this was the design we came up with that would let you, as an end user, do field replacement of the firmware and be able to assert that it's running what you think it is, but not completely lock it down. So the downside is it's not secure boot, but it is a trusted boot system. That was kind of the summary of what we've designed so far. Just wanted to open up for questions, and here we've got one.
I have a question for you. So you mentioned we have keys fused into AST2600 in there, and then you have a public key for secure boot, which is different from the one that is fused in. How do you link those two keys together?
Yeah, so it's measured after. So once your system's up and running, you do the TPM attestation thing, hand wave. That's not my field.
So one thing I can probably suggest the space is you can always sign the secure boot key, public key, with your own private key, which is fused in, whose public key is fused in. Sign that key, and then probably that basically verify that the secure boot key is something that you trust, and then you can move it further.
To grab a throw box.
If I understand this, there's one AST2600 key that you're fusing into a number of devices, and then you ship it to customers, and customers can put their own secure boot public key there. So there's one of those and N of those, and you can't sign those public keys with that other one. Otherwise, every customer trusts the same code as every other customer, and you have no secure separation between the customer workloads.
Or alternatively, you have to agree to sign each of your customers' keys with some magic specific to that hardware.
Or you take a public key with an order for chips.
Pardon me?
Or you take a public key with an order for chips.
Yes,
Yeah,
that's
so
what I'm saying.
if-
That's what I'm saying, exactly.
If you're building machines, you
which
could implement this one.
which restricts the resale of the next guy from doing that, right?
I mean, that's one way of actually keeping the trust all the way up, is what I'm suggesting. Probably you can have vendor IDs and those kind of things for different customers, and probably there are ways to do this. But it's something that we are trying to solve in the OCP security work group. I don't know if you're familiar with that. I'm pretty sure.
I don't go to those meetings, but yeah, the OCP,
Yeah.
there's people working at OpenBMC who are well down the OCP path, like the Facebook team? for
Actually,
instance?
I worked on OpenBMC for Facebook.
Oh, hello. Nice to meet you.
I've been one of the guys there. Anyways,
One more thing there, which is you need the TPM hashes at every stage on that embedded in a signed document on the website. So you need to be able to say, I've got HTTPS to go get this go get this document that gives me some structured data that's got the signature that's signed by that key, and that way, because right now you've got one step that's not measured, it's measuring itself, right?
Say again, sorry?
Right now you've got one step that's measuring itself, and if you can't trust that step, then you don't know. But if you know what the measurement's supposed to be, and you can verify it outside, then you don't have that problem.
So Peter, the idea is that the relying party somewhere else gets to see that stuff because they get to see your measurements.
Right.
Okay, so at some point someone does what you just said, and the formats for that stuff that you're describing are being discussed in a new IETF working group called RATS.
All right.
Remote attestation. So, and I think we have the same slide on somewhere there. So
Yay.
I wish we should, because this one's really good, and it was much clearer than the other one I saw yesterday.
I like it when somebody does something right.
Is there any document that show how AST 2600 keys can be provisioned, or this is like completely secret vendor knowledge?
I'm sure they'll publish documentation on their DA at some point. I haven't seen the documentation. They're still doing bring up of the chip. So,
Because based on analysis of that document, you can probably think about other ways of solving that.
yeah. So the ASP data sheet is available on NDA, so it's not a public thing. And the documentation as exists is still evolving. They're pretty early on in the process of the 2600.
Okay.
Is there hardware I can buy?
No,
Not yet. Will-
later.
They're still doing the chip bring up. They haven't written the manual because they haven't figured out where all the registers are going to be when they're done, right?
Right, fair. Well, I was going to say, how could I participate in this project without some hardware that has an AST 2600 with the right thing burnt into it, right? So
Yeah, they'll exist at some point in the future.
Okay.
But yeah, it's pretty early in the piece. I mean, no one's building machines with them yet because the silicon's only just appearing. The discussion around how this is going to work and that, we'll start having on the OpenBMC mailing list. I was hoping that would be happening before this presentation, but it hasn't happened yet. Matthew?
So in terms of the threat model you have about someone subverting the boot process, what is that? Are you concerned about attackers with physical access or just attackers who are somehow able to compromise the BMC some other way?
I don't think we're protecting against physical access.
So in that case, would having a default behavior of U-Boot SPL trusts, well, in this case, why do you load but not verify U-Boot? Does the U-Boot SPL not have the ability to read from EEPROM?
I can
That's a
probably
good
help
question. I can't
answer
remember,
Matthew's
sorry.
question.
No, it wouldn't. I mean, you could, depending on code size. So what we haven't done is gone down the path.
Okay,
of
so
how
I
much
guess
can you
my
put in the
question
SPL?
there is really, why does the SPL not verify U-Boot with the public keys that are in the secure boot database rather than just measuring it? Because if your concern is against, if physical attackers are out of scope, then the content of the EEPROM should be trustworthy.
Yeah, I'm not sure why that line doesn't exist down.
if what I think you said is why doesn't the U-Boot SPL use the secure boot pub key to verify the rest of the piece, even though it has no reason to trust that public key? It could still use that to validate it, is what you're saying. Okay, and so any attacker who could write to it could put their own public key in there, which is a goal because we want people to replace that. Okay, so the question would be, what attack does it defend against? And it would have to be some kind of attack where the attacker is not changing the stuff on the flash, but somehow changing the instructions as they flow across the bus or something like that, right?
So unless you have physical access, you could jumper, the EEPROM, so that it's...
Yeah, that was
Okay,
the plan, I
right.
think, with the EEPROM. It would be, you'd have to assert physical presence, put the jumper in to be able to rewrite it.
Right, so the point is that an attacker could who has physical access, or a user who has physical access can replace this with their own thing. An attacker can replace it, okay? And so the question is, in some cases, you want to give the owner isn't the user. So you go to a voting machine, right? You're the user. You have physical access, okay, but you can't open the box.
Right.
Right.
And so that was why I was asking whether physical access was in scope or out of scope. Yeah.
Right. But I could be alone with the voting machine, I just can't open it, okay? And
Right.
I could Trojan it.
But
Through
Joel previously said that physical access was not within the threat model.
No, you're missing my point. My point is I have Trojaned it through a software attack on the front of the console, right?
So you've got physical access.
So I've got physical access, but
Joel said physical access was out of scope.
Yeah.
But as soon as I open the box is compromised, and they know it's compromised, and they don't hand it on to the next voter.
But Joel said physical access is out of scope.
Yeah. If you have physical access,
I
you
would
can
like to
place the
add
jumper and
something.
change the keys. Yeah.
I would like to
Right,
add
move on.
something out here. I think the whole idea of having hardware root of trust is to safeguard ourselves against supply chain attacks, which is kind of physical attacks,
Against what attack, sorry?
supply chain attacks,
Supply chain.
where you have systems in transit, and attackers can fuse in or replace their images because they can jump the EEPROM, things like that. The whole idea of having trusted keys, keys fused inside the silicon itself, is to safeguard ourselves against that. And to answer one of the questions that was raised before, which is why do you need to have, why should we have separate secure boot keys for customers? I will not speak about AST2600 because I have access to the white paper that they have. But in general, the idea that we are floating with in the enterprise industry is we can have more than one key inside the hardware silicon. So whenever a vendor or manufacturer issues a key, you can revoke that and fuse your own key. The customer can fuse their own key. That's the way of handing off securely, either at manufacturing phase or at within your infra. That's how you can do it. So that's another way of actually doing a handoff for a cryptographic handoff of your trust from vendor to your customer.
When you're putting the second key in, how do you know that's a
Guys, just
legitimate
2 minutes.
user?
2 minutes left.
Oh,
Well, you don't have to put in the second key until the customer decides to blow the fuses. So you can let the customer do that. One more quick question about the threat model. So when you look at the trusted boot log on the relying party and you decide that the trusted boot has been compromised, what is the expected action there? So the BMC is the
Self-destruct.
way we're supposed to recover.
Yeah, I mean,
But the BMC was the mechanism for recovery. So
that's
if
going to
you
be
have-
your deployment specific. I mean, some data centers might say, okay, you don't get access to cryptographic materials to join the network. But that's up to the deployment. We're not solving that in OpenBMC.
Look up on the network for a new image. I mean, there are multiple ways to get to this.
You can't get to the network for a new image if you didn't boot.
I mean,
There's
yeah, I mean, this is an interesting conversation which does not have a definitive answer.
Yeah.
right.
Another one at the back.
Maybe a very quick question. Which of those components inside the boot actually talk to the TPM, and what are the things that they are reporting to the TPM? I don't know if that was on your next slide or...
That's the last slide. So from U-boot, we can talk to the TPM.
Which U-boot? SPL or...
Not the SPL, as I understand it.
So how do you connect the trust chain between U-boot SPL and U-boot if U-boot SPL is, U-boot is not started securely or verified, but only U-boot will talk to the TPM, there is a gap in the trust chain.
That's what I was talking about earlier, and I think you
Right.
verify it externally.
Okay.
I mean, the version of verified boot that Facebook has.
Sorry, we have to wrap up. Last two questions.
Last two questions.
One quick question.
Measure the U-boot from the SPL itself. So the SPL, we have a
Guys, could you continue the discussion in the hallways? Sorry.
One quick question. So one of the issues with BMCs is the life cycle is so
You're lost.
long for the development, and by the time we get it, it's pretty much broken, and there's nothing we can do about it. So can we try to advocate for QEMU emulation for BMCs and encourage
As in of the image, so you can
of
test
this
it?
whole stack, like
Yeah,
because we have
that's what we have. So if you go to,
including the pre-release,
yeah, it's on the internet.
including the pre-release NDA stuff.
Sorry. Yeah, so the 2600 we have, it's the kernel supports in mainline for 5.4, or will be in mainline for 5.4. The QEMU patches are on the list.
Okay.
So it's all out there.
So someone could run this.
They could run, let's say that the boot ROM isn't there. I don't know how we'd solve that, because that's a bit of IP inside the ASpeed chip. I'll talk to ASpeed about it.
Last question.
So last quick question. So I understood that the whole implementation for verifying things is done in U-boot in some custom way, which then would infer that on the kernel side, we have no way to actually do kexec. Have you considered actually adopting the EBBR standard for booting from U-boot? And how much, if so, how much would actually be missing to have real UEFI secure boot on that platform?
I'm not interested in UEFI. If someone else wants to implement UEFI as boot for it. So the Facebook guys did their secure boot implementation in upstream U-boot a couple of years ago, and that's what we're using. We could have alternate implementations. It will be running upstream U-boot, so anything that upstream U-boot supports could, in theory, be used in OpenBMC space. I am 1 minute over time, so I have to go. Thanks, everyone, for participating.
Thank you, Joel. So next talk is about UEFI and TianoCore update. It will be done by Leif.
Am I on? Can I be heard? Good. So that text said maximum 3 slides. I'm sure that was somewhere in the submission guidelines, but I never read them.
Don't worry about that. I think that it is a copy from previous conferences.
Cool. So it's a 20-minute talk, so having an agenda might be a bit overkill, but to set the scene, I want to talk about something we nearly managed to tie together and actually publish something before Plumbers, nearly. Some stuff that happened even before previous Plumbers, but I realized there wasn't actually any sort of UEFI update at Plumbers in Vancouver. So I do that, and I'll even throw in something new as well at the end. Or less abstractly, UEFI Forum is going to adopt what they call a code-first process, and that's the forum as a whole. It's not just the UEFI spec, it's UEFI and ACPI, and PI if anyone in here cares, but I sincerely doubt that. Other things, EDK2 stable tags, UEFI SCT being finally gone open source, and the UEFI interface support in U-boot. And towards the end, we have dropping the CLA for contributions to TianoCore, and also adopting SPDX and a license change. Anyway, moving swiftly on. So what the heck is code first? Isn't that just what we do? It kind of is. So let's explain why UEFI Forum adopts this name for the new process. I'll explain that by telling you about how the UEFI Forum has worked on specification changes or additions up to this point, and that partly depends on what the origins of the UEFI Forum was. So I've named this code last. This is not an official term, but I thought it appropriate. So the UEFI forum was basically set up as a neutral ground for a bunch of strongly competing organizations to collaborate together on, making sane standards so that things could interoperate. And that's both on the side of the hardware manufacturers, which is like AMD, Intel, ARM, but also like plug-in card vendors, AMD, ATI, NVIDIA, and those guys. And on the other side, you had the BIOS vendors, effectively. They might prefer different terms, but that's what everyone thinks of them as anyway. They're BIOS vendors. And peace was maintained here largely through the UEFI bylaws, which fundamentally focus on protections against submarine patents, because that's happened once or twice in the past. And the ultimate guarantee of this is the process through which specification changes happen. And inside the UEFI forum, this is referred to as an engineering change request, or ECR. ECRs are handed around in NDA-covered meetings, and companies get a say on whether they think there's anything in there that they consider an infringement. And at the end, if they haven't even said anything, they're given a 30-day deadline of speaking up. And if they do not say anything, then the UEFI bylaws mean that they have explicitly permitted use of this within the context of the specifications covered, and they will never enforce a patent against that. The problem is here that only after the specification release has happened is anyone actually protected by this. So that's kind of been the issue. So here's a scenario. You want to get support for a new specification feature into Linux, and you just missed the window of a UEFI specification release. So you got to wait another year for the next specification release, and crap, just around that time, one of your target distros released an LTS, and you didn't actually make it into the kernel for that. So you've just slipped by 6 years. That's the reality, and we've had some issues with around that. So going back to code first. Code first isn't actually even code first, but it's a change through which we can gain early formal approval of ECRs, and hence retaining the protections given by the forum bylaws. So the original process is not being actively retired, but realistically, anything that comes out of ARM, Intel, AMD, those guys, it's going to be tilting over strongly towards this end. And, okay, it's not just about the legal status, right? There's also the question of, is anyone in the open source community in the least bit interested in adopting an implementation of something that hasn't been formally qualified in one of the specification releases? So ideally, what happens is the ECR will be published as a first draft, and anyone can comment on it. At some later date, the UEFI forum members will sit down and vote and go, this is good enough, we're going to release it in this form, and we commit to not changing it beyond this date. And that way, we have a situation where we can actually give early opportunity for feedback on new specifications, not just from forum members, and we have a way in which we can say, look, this thing is going to be in the next specification in this form. And combined with this, this also lets us get a reference implementation out in those cases where we feel the need for having a reference implementation from day one. We can have a reference implementation published in a Git repository before the UEFI, the next UEFI or API specification has gone out. And this thing would have saved many sleepless nights during the ARch64 the entire ARch64 launch process. So, long story short, we're going to start publishing ECRs and reference code under TianoCore. It doesn't compromise patent protections, and we won't randomly change the feature between publishing the ECR and releasing the next specification. And that's the code first versus code last thing, which I guess, yeah, Ben? Mike?
So are the draft ECRs going up there as well, or are they going to be?
My understanding is that draft ECRs will be going up there as well, but there will be a point at which they're flipped. So when it's no longer a draft ECR, we'll update it so the document doesn't say draft anymore.
Nobody's ever done that before.
Anything else? Al?
Just to add on to that, it is affecting the ACPI spec as well. So it's not just UEFI. This is a fundamental change for the forum. It's taken many years to get to this point, but I still keep asking them, can we just ship code and then you specify it? But we'll get there. It's another 5 or 6 years. It'll be fine.
I think part of the issue of completely resolving this is that the UEFI bylaws doesn't really provide a useful way of updating the UEFI bylaws.
Yeah, no, that is exactly the problem. That is exactly the problem. Right.
Yeah, welcome to SPI.
Anyway, if you made it that far, here's a cute puppy who's nearly as tired as you are now.
Thanks, Leif.
Okay, and then there's the other random. So this is not necessarily stuff you need to absorb immediately, but if anything tickles your fancy and we don't have time to deal with it before this slot is over, then grab me in the corridor tonight and talk about it. So starting with the things that someone could have presented about in Vancouver last year, EDK2 has started releasing stable tags. So it's not quite releases, but we're getting there. We're putting some freeze period in and making sure that we get, in the week or weeks before we make a new tag, then at least it's just bug fixes going in. This is kind of giving people a halfway house behind, drinking from the fire hose or getting the not quite yearly UDK releases, which occasionally end up missing bits anyway. So introducing a period of soft and hard freeze of the master branch, and then basically it's just every 3 months, and if you look more closely, it's a bit of a wobble around Christmas because all us Westerners piss off for a month. But that's basically it. So especially for distributions, it's useful to know that this is something you can base updated packages on, and it's a cadence that is ongoing. But even for development, it's if you don't want to waste time trying to figure out whether will this actually even build, then if one of the stable tags don't build, then we screwed up and come shout at us. But that hasn't happened so far. EDK2 platforms does not yet have stable tags, and we're totally not committing to doing that, but we might unofficially be trying to do that by the time the next EDK2 stable tag comes around.
Why not on a per platform? Might make more sense. Do it on a per platform basis.
What?
Sorry. EDK2 platforms.
Yes.
Describe in one sentence.
EDK2 platforms is a repository that holds open source ports to various targets.
So stabilization of these things could be probably handled on a per platform basis, as in some are going to have stabilization points, some probably never will.
And this is one of the reasons why I'm saying that we're totally not committing to this. Yeah. It will definitely be, we have the option in EDK2 platforms because we have some maintainers who say, I don't actually care about tracking upstream, and then they can have a branch, and they can have a branch that we know it works against that EDK2 stable tag. And then we don't pretend that they're trying to maintain them. Also, oh, sorry.
quick question. Are you aware that QEMU have started to drag in the EDK2 source code as a submodule? And does that imply that they had some difficulties working with like the stable tags, or will it still be possible to, use random new stable tags coming out of EDK2 with that project?
Is Alex or someone in here? I'm aware that they have. I've not actually been paying attention to how. I don't think it had anything to do with them having issues with the before the stable tags or with the stable tags. I think it's just that they used to not ship EDK2 firmware, and now they ship EDK2 firmware.
I'm just worried that, they used to have like other submodules that then had like patch queues on top of upstream, and I'd rather, have that be avoided.
Well, I mean, it also depends what feature set you want to wrap into QEMU. If you want, HTTPS boot and secure boot, then yeah, that's going to pull in OpenSSL as well, and that's as a submodule of EDK2, and then that's not my problem. So, but it's just reality. Okay. Also ready in time for Vancouver. UEFI self-certification test suite was finally published on the 9th of October 2018. I think the first time we brought this up was basically when Linaro descended on the UEFI Plugfest for the first time in July 2013. They all just went, why would we want to do that? And then about 2 years later, they went, yes, we obviously need to do this. How do we do that? Oh God, the UEFI forum bylaws. And then eventually, basically, I'm not going to say it took 3 years, but it took at least 2 to actually get through and get everything published. So self-certification test suite is what you run on a platform to verify that your firmware basically conforms to the UEFI specification. It's not perfect, especially having been an entirely closed source development thing that people haven't really been able to review, hasn't helped it. But it's now public, and if you do find any issues, there's a public Bugzilla where you can report issues against. I figured I'd give a shout out to the U-Boot UEFI support as well. Started by Alice Graf, helped along by Rob Clark, and given a good boost by Heinrich Schuchart, who's currently maintaining that bit in U-Boot. Initially aimed to be just enough to run grub. It can now happily run iPXE, as well as with some additional patches from Takahiro Kashi, the UEFI self-certification test suite. So we can now actually have 2 independent, actually real independent implementations of the UEFI specification on which we can run the SCT, which is good stuff. Okay. Final slide. We are in the process of migrating TianoCore away from BSD2 clause and a custom contributors agreement to BSD2 clause plus patent license, SPDX, BSD plus patent. And just for reference, no, it's not that BSD plus patent. It is just a 2-clause BSD with an explicit patent grant. And again, this is to cover the same bit that the custom CLA used to do, and it's all about submarine patents. As part of this, we're also migrating to use SPDX tags across everything instead of regurgitating license in slightly different forms in different files, and that's all good. So we've already migrated EDK2 repository and the EDK2 platforms repository. Some of the other ones are lagging behind a bit. And if you got this far, here's another cute dog. No. It is the same sofa. Any questions on that? Do we have any time left?
2 minutes or so. 2 minutes.
Any random questions on anything? Cool, then I can run away. Thank you.
Thank you. Next talk will be SGX upstreaming status and challenges from Jarkko Sakinen. We are looking for Jarkko. Oh, here it is.
Does anyone have stronger fingers than I do?
I
think people will unplug it.
Okay.
Like very. Yes, it is. It is the smallest HDMI connector I've ever seen. That would help, yeah. Oh, no, we're good, we're good. Thank you.
One, two, three. Okay. Thank you. Oh. Okay. Okay, this is SGX upstreaming story. Actually, only the first slide contains the story. So, first, Skylake came in the market in 2015, and it was like the first platform from us that contained SGX. And we also did like the first attempt to upstream SGX patches in 2016, but it didn't go too well because only Intel can basically whitelist public keys for enclaves. So at LPC 2016, we had a meeting with Andy Lutomirsky, and I think there was Josh Triplett and Dave Hansen, and maybe I think that was the group, and then we introduced a flexible launch control which allows to run basically self-signed enclaves, and we made plans how to proceed from that. And exactly 2 years ago, a new series was started, and the first platform with the flexible launch control came into market in December of 2017, and since then I've been rolling out new releases of the patchet. Oh yeah, right now we are in the version 22. I think things are converging. We are not kind of returning back to the same things. Right now, the discussion is on LSMs, whether the LSM hook should be like a part of the like the initial patched or not. And we'll see. So enclaves are basically like well, they cannot be compared to the. They are not comparable to the full memory encryption solutions. They are more like comparable to like to ARM TEE, except they run in ring in a process address space. And so you can basically reserve a part of the address space for an enclave and commit pages to it from reserved memory area called enclave page cache. And then you can define entry points to the enclave. And only hardware threads that go through the entry points that are inside the enclave can access the enclave memory. If a code outside the enclave tries to access the memory, it will cause general protection fault. On the other hand, the code inside the enclave can read and write the memory also outside the enclave, but you cannot jump outside the enclave, and if there's like exception or interrupt or anything, it automatically causes an exit from the enclave. So if you want to do, let's say, a syscall, you have to exit from the enclave, do it outside from the enclave, and jump back to the enclave. So basically, enclaves do not have any powers to do syscalls or any way communicate with the rest of the system. And all the pages, when they leave from the CPU cache hierarchy, they are encrypted. So that prevents reading the memory from buses. And then there's also support for local and remote attestations, which means that locally enclaves can create private channels between each other. And well, and also enclaves can remotely attest to be genuine enclaves running inside genuine Intel CPU. These are the assets that we have at the moment. There's the kernel module that is part. Well, it's not like a loadable module, but still it's isolated to that directory that contains the whole framework for running enclaves. And then there's also like a simple self-test. And we have two devices for using enclave. One is for the enclave devices for creating new enclaves, adding pages to them and initializing them. And the provision file is for granting the remote attestation capability. So basically, that works in a way that you open the provision file and then use the set attribute ioctl to grant the access. And when you open that enclave file, the file descriptor is or you already have the enclave. The file descriptor has like direct binding to the enclave. Okay, so the kernel code is exactly 3,500 lines of code at the moment. The driver contains basically the ioctl interface. Uncle C and H contain like the enclave management code, and CLS on CLS C contains and H contain wrapper for this opcode called uncls that implements all the functionality to create enclaves and so forth. And then there's also support for overcommitting the memory, and so you can swap out pages from enclave page cache so that there's a version number in the EPC, and then you encrypt the page and a MAC containing the version number and the MAC of the page. So that is done to provide the rollback protection. And also the self-test is quite large because it contains, for example, a custom signing tool for creating the signature for the enclave. This is like the short breakdown of the key things, key features that kind of drive how the whole SGX core is implemented. I'm going to skip the overcommitment because there's no time to go through all the features, and it's kind of their least argument around that feature. The enclave construction starts by first reserving the memory range with mmap, and the way the enclave interacts with mmap is that you must the permissions cannot surpass the permissions of the pages that are in the range of the mmap. So when there are no pages recreated, you can only mmap with prot known, and that's how you reserve the address range. After that, you call the create ioctl that will create the first EPC page called secure enclave control structure, SECS, which contains like the measurement for the enclave and the address range and all the global attributes for the enclave. And then the pages are added with add page ioctl, which takes the virtual address for the page data itself, and sec info that basically contains the maximum permission for the page. And measurement mask that defines that which part of the page are measured, or is the page measured at all. The maximum permissions mean that you can basically mmap with an enclave with lower permissions than the permission defined for the page, but you cannot surpass the permissions defined in sec info.
enclave is here to provide a service, let's say maybe some encryption or certification capability or signing capability.
Yeah.
So you need to then give data to the enclave that the enclave will be able to access. Now, if you can't call into the enclave with a pointer because that's pageable memory, it will take page faults, and you said that was a problem for enclaves. So how do you normally exchange data in and out with an enclave?
There are special spaces called thread control structures that define the fixed entry points that you can enter to the enclave.
But that's entry points. How do you pass data in and out?
Well, you can pass pointers with, well, the enclave can read the data from outside, so you can use...
Wait, you can pin pages and pass them in, right? So we mark them to be unswapped.
Pinning will not guarantee that you don't get minor page faults. So you still need to be able to deal with taking a page fault. You have no way in user space to guarantee that you're not taking a minor page fault on a page.
We try as best we can, I believe, is the answer.
Yes, well, the way things work is that I mean, you mean a page that comes outside of the enclave, right? Well, the opcode that you use to enter the enclave takes so-called asynchronous entry point, and that is used for exceptions like page faults. So what the CPU will do is that there's a stack inside the enclave where it will save the enclave register state. Then it will okay, create like synthetic register state, and asynchronous entry point will point usually to an instruction called e-resume.
Yes, I see. Okay, so it takes
and the CPU will pre-fill the register with the right parameter for e-resume. So it will continue.
So the kernel will think that the page fault is coming from this e-resume instruction, will service the page fault, and will return to it.
Yeah.
Yes. Okay. Makes sense. Thanks.
Yes, exactly.
Just a reminder that just 8 minutes left.
Okay. Yeah, this is okay. So what flexible launch control brought was these new MSRs to where you can fill any public key you want, basically. Well, the einit instruction here has this 6-struct parameter that is used to provide the site measurement for the einit, and it will be compared. It will check that it's signed with that key, or if the MSRs are locked, you can, by the firmware, you could have like this launch enclave that is signed with that key, and it could create a cryptographic token. But it was decided that Linux will only support the unlock configuration.
So do we have any integration of this with the kernel keyring features? So right at the moment, I gather you write your key straight to the MSRs, and
yeah, right now everything is.
So but is there any plan in future so that I could look at a keyring and interrogate the kernel what keys it would run?
No, there's no plan, but I don't see that we would be creating any kind of roadblock for that.
Okay, just that was what I wanted to know.
I apologize if it's an obvious question for somebody who's more.
There's been actually some discussions to create like a whitelist of keys maintained by the kernel. So it's been in discussions.
So it might be obvious for x86 people who are familiar with it, but under what circumstances are the MSRs locked? I was under the impression that they are locked if you do secure boot on there. Aren't the MSR locked when you do secure boot?
Depends on MSRs.
Okay.
Feature control MSRs are always locked. But so that LEVR MSR is locked.
So when we talk firmware here, we think about something like UEFI runtime or SMM or something horrible like that.
I think MSR writing is locked down in secure boot mode, but the kernel can install to them.
Sure, but in this case, that means we can't set the keys.
But the kernel can. You say, I'm going to give it to Matthew.
Exit secure boot. We get access.
Right, so when you say in secure boots, the MSRs are not successful, what do you mean? So one approach is that dev MSR is locked down by the kernel, but that's not something that the firmware itself is doing. The MSRs are still accessible.
Okay, thanks. I did not know that.
It's not having a DTSEC exit.
Okay. So right now, the consensus is anyway that we only support the unlock configuration. The lock configuration would basically require a special enclave that would permit other enclaves to run. But I don't think we are neither creating any kind of roadblocks to introduce the support for the lock configuration later on. Okay, so here's the flow, how you enter the enclave. So there's e-enter that takes one of those TCS entry points and also pointer to that asynchronous entry point that you know the IRET from the kernel will return, and then it will jump back to the so it will point to kind of trampoline instruction. And once e-enter enters the enclave, it will replace the RCX with the address of the next instruction right after e-enter, so that you can pass that to the e-exit once you are done with your enclave routine.
Jarkko, sorry, how many slides left?
Okay, and this is how the TCS entry point looks like. This from my self-test program, and there's the save state stack that is used to store when we get this, you know, like interrupts and everything. That is used to store the register state. There's the field where the asynchronous exit point is stored. There's fields for FS and GS offsets, and then there's also limit FS and GS limits for 32-bit configure when running in the protected mode and not in long mode. But the problem is that enclaves generate a lot of exceptions because, for example, they don't support all the instructions that are normally available. So, for example, sometimes you might have to emulate some of the instructions. Generally, like the exceptions are like the part of the normal flow, and using signals is very inconvenient because they are process global and cannot be easily changed. So we ended up creating a new VDSO with a fix up handler, because it kind of resembles the kernel fix up table, but the handler is fixed because you cannot really create a variable pointer to a kernel function from user space. So it will always fill those registers when exception happens. So if you use that VDSO, instead of getting the signal, the VDSO will return, and you will have the exception information in those registers. You can also use e-enter, but then you lose all this granularity. So in practice, when you implement runtime for enclaves, you will want to use the VDSO. Okay, then we have, well, the access control is also like problematic part because because we are basically like, because you are not like executing or DL open an executable, but you're like building something a bit like with VM that you actually execute, but you kind of directly bind the permissions to in the same way.
Jarkko, just 5 minutes, please.
But still, even with Duck, you can, for example, have like a more privileged process that can build the enclaves and then pass the file descriptor to other processes, and they can then just mmap it. And this is not yet part of the main patch set, but we've also introduced this hooks for the LSMs so that they can add more granularity to that process. For example, make decisions based on the file permissions or something like that. Okay, that's all, folks. Thank you.
Any questions?
So there was quite a lot of discussion on the LSM side of things, so I'm not sure where that ended up. But one thing I'd wonder is how would an LSM know what to make a decision on? Like what information is it using to make a further access control decision? Or what?
Well, for example, in enclave load, it can reach through the VMA. It can reach the file where the page is added and make decisions based on that.
Okay, so but there would be some properties of that file or that page that would be security relevant. Yeah, that LSM would know anything about, like security labels, I guess.
Yes.
Okay.
And yeah, and same goes for this map hook is called when you call either mmap or mprotect, and it also provides binding the file.
Is the instruction the instruction to enter an enclave or resume one, are they privileged instructions?
They are ring tree instructions, but we still provide the VDSO because in order to provide more kind of robust exception handling mechanism.
So what's the best hardware to buy to run, to test SGX2?
For R&D, I would pick the Gemini Lake NUC for if you just want to kind of experiment with the technology.
Okay.
Anything else? Thank you, Jarkko.
Thanks.
And next talk will be about TrenchBoot, and Daniel Kipper will be presenting, probably I. May we start? Can you hear me? Okay. My name is Daniel Kieper. I work for Oracle, and I'm one of Grab upstream maintainers. Today, I would like to present something about TrenchBoot project. How many people heard about this project? Hi, guys! Shut up! Okay, thank you. No problem. Thank you. I prepared this presentation together with Ross Phillipson and Daniel Smith. This is requirements of the Oracle. And I will do a short introduction to the TrenchBoot project, and then I will focus on the kernel implementation of DRTM, which we are doing. So the TrenchBoot project is a cross-community integration project. This is no one project which it covers at least 3 projects. One is a bootloader, in this case Grab. The second is Linux kernel, and I will be discussing this today. And the third thing is uroot. The name was a play of dealing with muddy mess of trying to find a way to unify boot integrity. The purpose is to have to build a unified approach which will provide trust in the platform through launch integrity. Of course, everything will be built around open source projects, and this way we would like to provide unified dynamic launch approach for Zen, KVM, Linux, BSDs, and potentially proprietary kernels. As I said, I would like to focus during this discussion presentation on current secure launch for Linux. And this provides different strategies to build trust in the platform. Currently, the most common use is first launch, which establishes hardware-rooted integrity during platform boot. But there is a second option, which is called runtime launch. And in this case, this establishes hardware-rooted integrity during platform runtime. And using this second approach, it is possible, for example, secure launch a kernel for upgrade to do some runtime verification, or secure launch to do update shutdown the kernel. How the boot flow looks like. So at the beginning, we have UEFI, then UEFI can run IPXE, and IPXE can run shim, and then we have a bootloader. Currently, all developments for dynamic launch are done around Grab, and there are some features which currently exist in the Grab. First of all is the verifiers framework. It is code on top of which we provide features, for example, UEFI shim driver, TPM drivers. And here, the boot path split in 2. First thing is AMD implementation, and this starts from SKInit relocator. Then SKInit instruction is executed. Control is passed to secure launch, which is called in our case landing zone, and landing zone passes the control to a secure kernel, which is intermediate loader used to do the various things like measurements, various checks, etc. And if everything is okay, control is passed to the operating system. Situation looks similar in the Intel TXT case. We have TXT relocator, then center instruction is executed, and control is passed to the ACM, and everything is okay. Then DLME as intermediate loader is executed, and of course you can do the same things like in previous case, and pass control to DOS. Some blocks in this diagram are optional. For example, there is no requirement to to have a UEFI. You can run dynamic launch on non-UEFI platforms. Also, you can. There is no requirement to use iPXE or secure boot or SRTM. So some parts optional. It depends which parts you will use on your use cases. If you want more about the TrenchBoot itself, Daniel Smith and I did a presentation about TrenchBoot, how it works in general, general ideas behind the project, etc., etc. During Linux Security Summit in North America this year. You can find slides at this link, and I hope that video will be or is published. It's published. Okay, that's nice. So, as I said, let's focus on a Linux kernel implementation. This feature is prepared by a colleague of mine from Oracle, Ross Phillipson. So I know how it works in general, but some details are not clear for me. So I'm trying to explain and ask for general feedback to this idea. So TrenchBoot Secure Launch feature in the Linux allows the starting of post-launch MLE stage of secure late launch to establish DRTM. The code is split into various logic blocks and phases, and I will be discussing this in such way. Currently, Oracle focuses on Intel TXT implementation. Free MDEP company, thank you. Company focuses on EMD implementation. As far as I can tell, it works. In case of Intel TXT, it boots, but we have some difficulties with quite strange because system boots, and at some point during network drive, when network driver loads, then system crashes. We don't know why. We are trying to investigate what is happening. So, entry point. We can compare the SL stub, which is just entry point to the secure launch, to the UEFI stub. This is just minimal, minimal. What's happened? Oops. Have you said that? Oh, that's bad. Okay, continue. So we can compare this to UEFI stub. And the first bit which is executed is SL stub entry, and it lives in a head text section. This is just a small piece of code because this section is tightly organized and we don't have much place to do different things. So we jump immediately to something which is called SL stub, and it lives in the TXT section. And SL stub continue execution. It loads, it initializes BSP CPU upon entry from TXT. We do this accordingly to the TXT specification. Then it means that we are loading GDT, check and prepare some parts of TXT heap, enable some interrupts, wake up APs, and restoring their states, and then park all APs in safe location. I will discuss this later. And after that, we are restoring also some MTRs and MSRs, which were covered during the launch. And after SL stub, the control is passed to the SL mine function. It is called from compressed kernel. And the main idea of secure launch is that everything which is executed has to be measured. So this part of code takes all boot params, command line arguments. Also, it can takes initramfs, measures into relevant PCRs, and also validates TRRs. And After that, control is passed to the SN/launch setup. There are some things which are not needed to be done in the early step. So we have to verify the platform whether a measured launch was done via secure launch. We verify VTD PMRs, reserving some regions for TXT heap, TXT registers in E820 map, validate E820 map against MDRs, and also provide a ACP DMR table to Intel IOMU driver. SMP bring up. As I told earlier, we park the APs in safe place. As far as I can tell, Ross worked very long time on this piece of code. It was very difficult to start the APs and in this mode because you are not able to simply send init to the APs and to do that in usual way. So we have to leave APs in waiting busy pause loop and send NMI to the waiting APs and vector them to code which is similar to 16-bit startup code, but it contains some differences which are needed for secure launch. And then after that, further startup continues as usual. And last thing, security FS. We have to provide TPM log to the applications. So it was decided that the most convenient way is to do that via security FS. For example, IMA provide some logs via security FS. So we have to add some code to the security FS to expose this TPM log to the application. I think that's it. And I'm looking for comments to our approach. As I said, I know the rough idea how it works. We would like to get feedback from you. Are you agree with our approach? Do you think that it makes sense, or maybe we should change something, or maybe something is done and we are, let's say, we're reinventing the wheel? Joel.
So what is your object in doing TXT? Is it to get the dynamic root, which means the TPM reset of the registers?
Yeah.
Or is it to prove security of the boot? So if it's the former, there are other ways of actually doing a dynamic root that don't involve TXT. The problem with TXT is this handshake between the attestation server and the CPU, where the CPU itself does the TPM reset. So for the container case, where it's impossible for us with thousands of containers to use a physical TPM, the dynamic root transition is actually transitioning from a hardware TPM to a VTPM and then one VTPM per container. Now, I'm not saying it's a better way for virtual machines, but it's certainly a way that works for containers and is scalable and gives us the dynamic root of trust.
Okay.
And what? Well, we don't have to rely on any Intel crap, which doesn't seem to work on half our machines. This is the big problem we've had with TXT.
Our approach is this is not a kind of secure boot. Of course, we would like to be sure that dynamic launch assures us that the platform is in correct state as we expected. But we also going to use, to some extent, secure boot as a check that we have booted correct kernel, and additionally, we also want to get some keys from the secure boot. So we are relying on both technologies. I hope that it replies to the question.
So I believe the objective of TrenchBoot is kind of unify the ecosystem of the RTM, which exists there in hardware. This is approach, and if I understand that there are different ways of doing TRTM, but how this is tied to hardware in that way, in your case?
So the hardware tie is through static root does the boot up all the way to the VTPM. Then VTPM, once it actually verifies through the attestation server, which is sort of the attestation server actually authorizes key release, and then we do boot up the VTPM and then connect the containers to the VTPM. So the proof that you got up through the static root is actually signed into the VTPM and then is used as the first measurement. It's almost the same way that TXT works, except it's open instead of being Intel proprietary. And it's not hardware-based because it's the VTPM runs in software.
Oh, okay.
Yeah, I see Rich wants to say something, but that requires SRTM, which requires boot, and this approach can be used runtime, so which would not require reboot, which in some cases is very expensive.
Well, so it only requires SRTM in the same way this one does, because you still have to have the static root verification through the attestation server, which we also do. So effectively, the dynamic transition is about the same with this approach as it is with ours.
We're also going to use SRTM in some cases.
Yeah, my dislike for SRTM, I'm from open source firmware ecosystem, is that like there is no implementation which is really open, maybe except Google's stuff, because like Intel Secure Boot or Intel BootGuard requires proprietary tools and NDAs, and the same thing is with NXP, the same thing is with AMD.
Well, Secure Boot doesn't, but some of the TXT does.
Well, BootGuard uses TXT way before you see it.
Yeah.
Yeah, yeah. But still, everything to provision SRTM, you need tools like NDAs with vendor. So that's kind of problematic. And to say a little bit about the AMD implementation, it can be fully open. So we already did fully open implementation without any binary blobs.
So our static root isn't really a static root, because the IBM attestation server actually takes the entire boot log, parses it, and makes sure everything is done, and then it verifies the hashes of individual components, and it has a dynamic range of hashes. Yeah, it has a dynamic range of hashes that it'll say yes or no to. So effectively, the attestation server dance is the same as yours, and it does a dynamic transition based on a range of possible hashes in the boot log. Yeah.
Yeah.
So good for open power.
Well, no, this is the IBM attestation server, works for any architecture.
Is it open?
Yeah, it's published on, I'm afraid it's on SourceForge, but it is published. You will never find it, no. It's been maintained by Ken Goldman, and he has a particular affinity for SourceForge.
Oh, okay.
A question about the VTPMs you were just mentioning. Are those in QEMU?
Well, they can be. So it depends what you're launching. If you're launching a virtual machine, chances are you want your VTPM to go via QEMU. But if you're launching a container, you don't really have a sort of intermediate emulated BIOS, so you have no need of QEMU in a container, and you just connect directly to the VTPM channel. And you can do this either by an IP connection, which the TPM accepts, or we can pass the VTMX device directly up into the container and do it that way.
Have you considered enclaves, hardware enclaves for the VTPMs?
No, because we want them to work.
But they're fairly easy to attack, right? And then you lose the entire point of attestation. They're trivial to attack. So you might as well not bother and save yourself the work.
Well, like I said, we're basically looking at protecting the runtime environment of the host. If we can keep that protected, the VTPM is running in the runtime environment of the host, so all the secrets that it has are safe in that environment.
How are you protecting the runtime of the host?
It's by static boot and all sorts of other security protection mechanisms that are usual for cloud.
Like,
static root of trust and
like
other
what?
things. Like things like the sort of the QRadar, and I can list a load of IBM proprietary technology if you want, but it's about the same as the proprietary technology that all the other clouds would list.
Got it. Okay, all right, thank you.
Yep.
James, do you use SWTPM for VTPM too?
Well, yeah, it's software TPM. VTPM is a software TPM.
Oh, yeah, okay.
So when you do the KExec
Yeah.
Or in the case where you're doing a KExec and then you're reestablishing.
You mean from? Oh, sorry.
Sorry. So you mentioned the idea of being able to do.
From.
No. So later. Sorry, maybe I misunderstood. But one of the advantages of DRTM was that you could reestablish the trust as a later point.
Yeah.
So,
yeah.
for instance, when KExecing.
Yeah.
So when you do a KExec, when you do a DRTM, are you then still having to look at the static root in order to verify that the firmware state was at boot time what's expected in order to attempt to gain some sort of trust in SMM?
I know what you mean. We discussed this idea with KExec just roughly. We haven't thought in, but I think this is good point. This is a good point.
So I believe this is also a question to James because Petit Boot does KExec in a measured way.
It does KExec.
So I believe this applies, the Matthew question applies to.
So I'm not really a power expert, but you're right, it does it, but it does it in a measured way through effectively a static route. So we believe it can be done. It's just that the more KExecs you do, the further away from the real static route you get, and the more difficult it becomes.
Mike, Peter, Mike, is it a problem for you if we are running over? We are running over.
I believe your VMs are initialized with a static root,
Nobody
and you're
cares.
running
Okay.
Petit Boot
We can go.
immediately from there.
Well, this is the P series. I bet you Ben knows more about it than me.
Yeah.
I just know what Mimi
He's
yells at
sitting
me,
right
and
next to you.
I'm an x86 person who's forced to deal with it occasionally.
Actually, I have not worked at all on any of the security part, but Petit Boot is only used for the host. The VMs use some other things.
So you've just initialized the root, the static root that Petit Boot is running on, or rather running at.
Yeah, but Petit Boot is slightly more complicated than that. It is a Linux booting Linux system, which is why we need KEG.
Yeah.
All right, we might have to leave it there. It's break time now. Thank you, Daniel, for your talk.
Thank you, guys. Wait for another flower. My wife and one guy finally asked, "Are you German?"
Oh, really?
I
would not.
confused.
Well, they don't know very much.
German. It's even different family language, like it's.
Well, it is, I know, yeah. So I was going to ask a question, though, but I heard recently, but maybe you know the answer anyway. Maybe Polish is similar for all I know, but I don't think so, actually. No, but in this specific point, which is that it doesn't matter the order of the words in the sentence. Is that true in Polish as well? No. That's what I didn't think that's true in Polish. There's reverse Polish notation. We know what that is. So that's why I think Polish doesn't care about the order of the words, right? But
Cool joke. You can play the order of words doing something.
like there's different emphasis in Russian by putting the words in different order, but the sentence always means the same thing. Right. I'm actually complaining about it. I'm complaining about a document specifically. Oh, yes. Roots of trust. It's actually we're arguing about roots of trust. Okay. And if you change the word of the order of the words, they're trusted roots. Trusted roots are anchors. Anchors. Right. And I have a lot of problems with these roots of trust words that bunch of this and other documents have come up. I'm like, guys, you're really confusing people, and it really takes a lot of brain power to unconfuse yourself each time you go through this. And like, really, so it's just bizarre, right? It's what it is. Should be immaculate measurement. Or something like this, because you have no way of measuring yourself, right? And so immaculate, is that word? Do you know that word? Immaculate. Jesus was born by immaculate conception because Jesus' mother was not touched. Right? Mary was not touched. Right? It's the same thing. You just suddenly God creates trust.
But you have to trust this kind of head of God is this instruction. It's like hardware, or it's like some hardware.
No, it's not. The first instruction that's running, the first thing it does
because it measures its own code. Okay. And writes the first measurement to a PCR. Okay. And so it gets stored for later on for attestation as part of the measurement. So then you measure that this part booted correctly, right? And but that code itself has not actually been, code has not been verified before it ran. It could do something else, but then it wouldn't measure it. Oh yeah, I know this.
That's nice.
But why is it all written out in so, you can do it with, this is a differential form, and why isn't it done with del cross products, dot products? It's much more complicated than these things. So I actually have a plan to get that tattoo.
Yeah.
Okay, but I'm going to get it. So the part of the difficulty is, right, so there's the integral form of Max's equations, right, they integrate, and there's the differential form, which that is, which usually is a del dot or del cross, right? On the one hand, so 4 equations, 4 limbs, okay, have a degree in physics, right, it actually means something to me, it took me a long time. I want to get Chinese characters that say this guy is an idiot, I see a lot, I've seen like, a woman with just has stars, just kind of coming down from her ear. Like, that's kind of cute, right? It doesn't really mean anything, just kind of cute, right?
But you just wanted to just blow off, blow off our work to be tattooed on its skin.
I wanted to put something on my skin and I wanted it to mean something to me, and it takes me 20 years to think about what that is. Okay. Okay, so now that I know that, right? But now I don't know whether I should get C. Differential is simpler, really easier for them to get right. Okay, but it's not as beautiful. Integral form, 3 integrals, the surface, volume integration, right? Of course, that one, the one about magnetism, explains magnetism, and has to go here. Okay. Because the right hand. Right? I mean, originally I was thinking, oh, it needs to go on a leg where there's lots of space, but no, it has to go on this.
That's crazy idea.
So I do know a woman I went to high school with, and she helped me think about what I wanted of it, chatting on Facebook. And I said, good, and you can do it, right? Because she's been a tattoo artist for most of her adult life. And no, because I don't work to do that anymore. No, and I live in Buffalo. I went, when did you move to Buffalo? It's Facebook. How do I know where people live, right? Right? He goes, oh, 15 years ago. I'm like, oh, is that when you stopped doing tattoos? And he goes, yeah. I'm like, oh. I mean, she was literally in high school, 17. Smartest woman I knew, right? And could have gone to her sister went to MIT and did physics, right? She had higher marks. So what did she do? She got a job doing tattoos because she liked that. A couple of years later, I said, so what did you do today? Oh, having babies, doing having and putting on tattoos, putting on me and other people. Okay. Okay. But is that like prioritizing people? I prioritize the babies above the tattoos. All right.
People have their goals.
They have different goals in life. You know what? She's smart enough to figure out that her goal was not to be, not to do other things. She wanted to do what she wanted to do. Okay, well, that's really cool.
We respect that choice.
Yeah. So where do you guys work and live?
I work in Oracle.
Oracle, I know, but that could be anywhere.
That's true. In case
Where's your office? Where do you work?
I have my own home office.
Home office, okay.
I work in Poland in Warsaw capital city. I work from home because I'm only one guy in Poland in the team, so I do not go to the office. It's boring sometimes. I like to work from home, but it's boring.
Mostly I'm Yeah, and it was winter time, and it's dark and cold. Okay, so people at the nearest, people at the nearest pub, they know who I am. I know my name there, okay. Wondering whether or not I should acknowledge them in a document. They helped immensely writing this document by providing unhealthy amount of cola. Right? It's like, do you want a refill? Do you want a refill? And they just bring me a refill. I'm just sitting there and like, sometimes I'm there like 5 hours. I show up at 12:30 and I leave at 6 p.m. Okay. Right? When the place starts getting busy again, and I'm like, oh, I should go home.
If you will try that for too long, that health problems guaranteed.
Yeah. Well, yeah. Well, no, I'm diabetic.
It's very successful, I would say. It's a very successful event. At some point there were more people than on OSFC.
But you know, it actually would be good for people like I know very little about what's actually happening in Linux in Secure Boot. Okay. Okay. And there's probably some people who are the opposite. Okay. Okay. So actually, what we do is if you might actually we're having a 5-minute talk with, 3 slides. Here are some terminology, and here are the people. Okay. Here are the people in the universe. I don't know.
Yeah.
Right. Just because I think part of the point is people who don't normally care about such a thing come to micro-conference and go, oh, this is what's happening.
Yeah.
Right.
Yeah. Yeah. I wonder if this would be continuous. If this will last. You mean about microphone? About this microphone. If we do this. Yeah, I can do this.
Yeah. I think you update some stuff like that. Right? Like find out
Daniel.
what so you covered it all.
Okay. It's on.
Pretty fluently, but in terms of when I speak as a speaker, it's quite no.
Folks, we will be starting in a minute. Okay, we will start, and as I said earlier, we'll have a TPM block right now, and it will be started by James, TPM to security interface of bus interposes. James.
Okay, so the thing about this talk is I have no slides whatsoever. What I'm showing is actually the documentation from the patch I just posted to the TPM list, nothing else. But what I wanted to convince you of, first of all, is that with TPM 2.0 we do have a security problem. TPM 1.0 didn't have this problem because with TPM 1.0 there was no way of sending un-HMAC'd insecure commands. Well, actually there is a way of sending un-HMAC'd insecure commands with the TPM, but for most of the commands they required an HMAC and didn't make it optional. TPM 2 made security effectively optional in everything, and to get TPM 2 into the kernel, we actually took this option, and all of our kernel to TPM communications are completely insecure. Now, in theory, the kernel is talking directly to the TPM device over the low pin count bus, so this shouldn't be a problem. We should, in theory, be in a secure environment. Unfortunately, a group of Canadians came up with something called a TPM Genie, which is a snooping device that actually sits between the kernel sitting up here, and we talk over the LPC bus to the TPM. And the TPM Genie can just sit on this bus, and it can actually intercept all of the LPC transmissions. It can actually remove transmissions from the bus, so it can stop things getting to the TPM, and it can intercept communications for the TPM and actually substitute its own replies. So this makes it the perfect snooping mechanism for something which is completely unsecure. Now, the good news about TPM Genie is that this thing is a hardware device. Someone needs physical access to your machine actually to place it on. But obviously for devices that are placed in public, like voting machines, this is a significant problem. Hardware security now becomes a significant problem with the TPM. And if you think you can guard your laptop and get it to work, there's unfortunately another problem which recently materialized in that this low pin count bus is actually controlled by the BMC. If you could modify the BMC firmware, you can actually make the BMC also be a TPM snooper. And as we know, modifications of BMC firmware are now a de rigueur attack of almost everybody, so nobody's laptop in this room is now safe from the potential that this thing brings.
Does the TPM Genie require soldering or breaking with traces?
It depends how your LPC bus is configured, but most of the time they've actually just been able to attach it to the LPC lines. So it didn't require soldering, it just required placing on the lines.
When you say BMCs in the laptop case, do you mean management engine or?
The baseboard management controller itself is connected to the LPC bus.
The laptops don't have those.
Yeah. Oh, sorry, I'm thinking of the server case.
Yeah, okay.
So LPC is also like kind of Infineon probably will not continue the line of LPC. So it probably SPI or some other bus will be more popular.
Yep, that works. The SPI bus comes out of the BMC as well.
Okay, I'm saying if Genie is for SPI also.
Yes, it is.
Okay.
So the basic problem with all of these buses is because they're low bandwidth, low pin count, low everything, they're basically small serial buses. It makes interception very easy provided you can get physical access to the bus. Or something that sits in the middle of the bus like the BMC for server class machines. So the solution to this is to try and come up with a scheme where we can defeat the tampering as far as possible by HMAC and encryption. So if we HMAC and encrypt as much as we can going into the TPM and coming out of it, the Genie that's monitoring it could throw the request away, but it can't fake the response because it doesn't have access to the HMAC parameters. And if we see something that doesn't get a correct response on the TPM, we know that there's something up. So we can detect the fact that we've been tampered. So the object of the TPM security patch that I just sent to the list is to try and actually get as much physical security for the TPM we can, and to provide a foolproof method for detecting that if we got hacked in the boot sequence, we at least managed to detect it. Yeah.
Why can't the BMC just do a man-in-the-middle attack and talk to the TPM on your behalf? So you think you're talking to the TPM, you're actually talking to a TPM emulator on the BMC.
It can, that's the problem.
So
But if it can't fake the response back to you, you detect the man in the middle. That's the point.
How do you know it can't fake the response?
Because if the request and the response are both HMAC'd, the seed for the HMAC is not known to you, the man in the middle. And there's an elaborate sequence I can use from user space to prove it's not known to you.
How do you get the seed?
Okay, so this is going back to, there's actually right at the bottom of the document, there's a discussion of how we do this. So this is establishing trust with the TPM. So
but you may be establishing trust with what you think is the TPM.
But each TPM contains both an endorsement key and an endorsement seed. So one of the things you have to do when you first get your laptop is to extract the endorsement key, which corresponds to the endorsement seed, and use quoted values to actually attest to the fact that you're actually talking to the TPM.
You need to store some secrets you got from the TPM.
It's not a secret, it's a public key certificate,
public key you got from the TPM,
which is signed by your TPM manufacturer, yeah.
So before your BMC is cracked?
Ideally, yes.
Or like bypassing the... Or you unsolder your laptop, desolder BMC, then you connect to the TPM, then you extract the keys from it, right? Because if you don't know if BMC was hacked yet or not.
Right, but David's theory relied on the fact that the BMC would intercept the communication and talk to the TPM. So if you're talking to my TPM that's physically in the machine, you have no choice but to give back my certificate. So the only way that a BMC would be able to give you a fake certificate if you're a man in the middle is it would actually have to have access to a different TPM that was manufactured by the same manufacturer. The certificate would then chain back to the manufacturer's certificate. It's not impossible, but it's an elaborate attack. It can be done.
So you can basically provably verify that a key came from a specific TPM. But obviously the problem is that if at some point your boot process has been compromised, you can't guarantee that the operating system that's doing this validation is itself correct. So doing this really solidly requires remote attestation, at which point the remote system verifies that the endorsement key chains back to the TPM manufacturer. If you've got a platform certificate, you can then use that to verify that the endorsement key corresponds to the serial number of that system. And then you can have a remote system, say, send you this information to your cell phone or something, and then verify that this matches what's printed on the bottom of your laptop. At which point you can be reasonably certain that the key, which you can then verify chains back to the EK, is legitimate.
Yeah, and the good thing about the BMC is that its flash area is reasonably small. It does actually have access to, it can get access to the memory bus. It could, in theory, corrupt the kernel. But to launch such a sophisticated attack is probably not within the bounds of feasibility. So at the most, what it's probably going to be doing is either snooping. It's basically probably going to be snooping, so getting hold of your secrets. Remember, some of the secrets that come out of the TPM on early boot are seeding the random number generator, which means every key you generate from urandom from thereafter, you may be able to predict. Fortunately, the TPM isn't the only random number seed, but knowing what the TPM put into the entropy pool helps you actually work out what the sequence of random numbers coming out of the kernel is, for instance. But the way we would actually detect whether we'd been compromised is to use a mechanism called the null seed. So a TPM has 4 different seeds. It's got an endorsement seed, a platform seed, a storage seed, and something called the null seed. The 3 platform, endorsement, and storage are all permanent to the TPM. They can be, you can issue a TPM command to change them, but if you don't do that, they persist across boot. The null seed doesn't persist across boot. One of the attacks we actually have to worry about is something sitting on the LPC bus can actually assert the reset line, which means it can make the TPM think that we've actually done a power on reset, in which case everything goes back to the beginning. So one possible attack is just to wait until the TPM's collected all of these PCR values, assert a reset, and then feed your own bogus values into the TPM so that the PCR measurements you get are not what the TPM actually measured on boot.
So as far as I know, the PCR 17-22 got DRTM prepared flow, so they behave a little bit different. So the initialization value is -1, and then when DRTM happen, first is zeroed, and then there is measurement there. So this prevents this attack because it will be, after reset, it will be -1.
Right, but that just means you can't fake the TXT transition easily. unless you can get access to the special TXT instruction. Yeah. So I haven't actually looked at that attack. I don't know whether it's feasible for the BMC or not, but I assume you'll be looking at it after this. So the point is that since we tie everything to the null seed and the null seed changes on reset, what the kernel is going to do is use the null seed or the elliptic curve derivative, the NIST P256 elliptic curve derivative of this to establish a secret session with the TPM. If the TPM gets reset after that, the null seed will change. The kernel will store what it thought was the null seed, the null public key from the TPM in a location, and that means that it will be able to attest to this in user space at some point in the future, and if you want to defeat this, then you have to get into the kernel and try and change that null seed. It's not beyond the bounds of feasibility, but given the sort of low memory capabilities of all of these devices, it's difficult. Yep.
So how does the null seed get passed up to the kernel? As in, so at what point do you commit to using a particular null seed?
So the
what
first
stops the attacker from waiting until you get to a certain point in boot, then doing the reset, then remeasuring stuff up to then before the null seed has been given to the kernel?
So this is my attempt to do poor man's attestation using a remote server. The kernel itself, the first instruction it sends to the TPM is get the null seed. But obviously it can't have any security doing that because we don't have any trust established with the TPM. So it just believes the value that it's given. Oh, it actually gets the null key. We can't get the seed, but it gets the null public key. And then it just squirrels that away, uses that to construct trust, and uses it forever after, and passes it up to user space as this was the null key I was given. It is then up to user space to actually ask the TPM to quote that null key back to you, verify it's the same null key, and use the endorsement certificate to verify the quote. So if that all passes, then everything should have been good from boot.
So how about the case where during boot, there's a malicious bootloader, so Grub's replaced with a malicious bootloader. And before Grub starts the kernel, Grub deliberately halts for a few seconds, at which point someone comes in, resets the TPM, programs legitimate values, and then goes to the kernel. At that point, when the kernel grabs the null key for the first time, it will be the null key post-reset as opposed to the null key pre-reset.
Right, so the defeat for this is something I was trying to propose to the UEFI security team, which is that this getting of the null seed should be chained all the way up through the firmware. So in theory, what should happen is that UEFI, in its first communication with the TPM, should also get the null key, and it should hand this value off to the kernel, at which point we will use this value as the null key and so on, and actually verify the TPM still gives us the same value and so on, which would provide an unbroken chain all the way from the static root of trust that sits in ROM. But this UEFI piece is not implemented. I still have to socialize it with the UEFI security subteam. So I have a theory as to how to defeat that, but right at the moment it's not in practice. Okay, so the null seed is how you verify in user space that you managed to get a correct boot by using a TPM quote of the null key and verifying that it's the same one that you booted with and the same one the kernel's presenting to you. The way you defeat the snooping attacks is to encrypt all significant responses. This means that the random number generator response must be encrypted on return. So anybody snooping the LPC bus can't see the random number the kernel is using, for instance. It also means every TPM transaction has to be HMAC'd so it can't be interfered with. And HMACing can be done in the TPM2 by establishing a session with the TPM using the null key again, which establishes a secret. You use a nonce and a secret to do the HMAC, which means that it's impossible again for the snooper to tamper with the command or tamper with the response. So effectively we can, if we use encryption and HMACing, we can get the kernel into a state where if it can't prevent tampering, we can at least detect it, or at least we have a good chance of detecting it. The attack where you actually prevent us from detecting it has to be a phenomenally sophisticated one. And realistically, all I really want is people to think about the problem and either agree or disagree that if we really want to solve it, this is the only way of doing it. Or write your own way of doing it.
So I think the other way of doing it is just to use firmware-based TPMs rather than discrete TPMs. if we're doing everything inside the chipset,
How
then
many people trust the Intel management engine here?
it solves this attack.
It solves this attack. I don't disagree. If your TPM were based in an enclave and so what Matthew is saying is that the problem is actually the bus, right? So a physical TPM has to be connected to the system over a bus. A virtual TPM is effectively part of the system. It can communicate over different communication channels that are not subject to interception by things like TPM Genie and the BMC. So this makes an emulated TPM in this instance more secure than a physical TPM because the communication channel is theoretically not one subject to probing. I'm sure if we advocated for all firmware TPMs, at some point somebody would find a way of actually attaching something like a Genie to a firmware TPM. There is always some method of seeing the communication. It may be a sort of separate enclave sitting somewhere. It may be hacking into the enclave. I agree theoretically it solves the problem. I just worry about practicalities.
There's another situation that people have been there's another solution that people have been talking about implementing, and that's getting rid of the bus. There are serious discussions of putting TPMs on the CPU package.
Well, that's equivalent to the, once that's done, how do you know whether it's an emulated TPM or a physical TPM?
It's still got an attestation key.
Okay, so, I mean, in theory that would sort of work as long as you trust, at some point there's got to be an internal bus inside the CPU, which is probably run by some sort of CPU firmware.
You've at least up to
you've raised it up to
moved the threat model for people who can decap a CPU and alter it.
Well, I was more thinking of people who could work out how to do a firmware attack against the CPU in the same way they've done against a BMC. I mean, if we discussed this, 10 years ago, you'd have told me that firmware attacks against the BMC just couldn't happen.
I would not have told you that.
Well, you might not have done, but everybody else would have done. Okay.
Yeah, but you have that problem with changing your motherboard.
Hang on. Microphone if you're going to continue talking, or hand it over to the next guy to ask. And the guy with the microphone is behind you, so.
Okay. So, yeah, I mean, it's a good idea about having a TPM on the CPU package, but what if that's tied into the Intel management engine? I mean.
Surely the important thing is that systems where the TPM is separate already exist and will need to be supported.
Yep. Okay, so David was next, and then you can throw the, you've got a microphone, so you,
okay.
No, but David was the.
In the topic of FTPM, so we already have exploits in EMI, so this will not work for that. But what about, I read in TCG specs that this is out of scope of specification, and platform should protect that.
Yes, so effectively we are the platform as Linux kernel, so we are now trying to protect this.
I'm saying platform vendor, which hardware vendor should protect that you cannot intercept.
Yes, but they didn't, so we're stuck.
Yeah, that's true.
It's fine to say it's somebody else's fault when you're hacked, but it doesn't help the fact that you're hacked.
We are running out of time.
Okay, any other questions? Yep.
So if I get it correctly, the one thing is doing just TPM parameter encryption from user space, which you can do right now by just talking, establishing a session with a salted.
We're doing TPM parameter encryption and HMACking from the kernel. So the kernel, because it doesn't have a TPM security library and previously did none of this. So what I had to do to get this to work was actually rewrite all of the security primitives that sit in the user space TPM libraries to conform to the kernel's crypto system so we could actually get it all to work. It turned out there was actually a bug in the way the kernel does elliptic curve handling. So if you look, I'm now a crypto person because I have 2 patches in the crypto subsystem fixing this.
So why would you need the kernels to do it if user space can do it just as good?
Because user space is not brought up from this has to be done from the initial boot when user space doesn't exist. As part of the boot sequence for a kernel, what we will do is ask the TPM for a random number to seed our random number pool, and we will start to do certain things with the PCRs to measure and change them. So we're actually acting on the sort of static root of trust. So the static root of trust comes up through measurements of the kernel. And IMA wants to use this for actually doing runtime measurements of the binaries. So if we have TPM security, it has to start in the pure kernel TPM instructions, right, which have no user space to be able to use them.
as the kernel boots, it has to talk to the TPM, and it can't talk through user space because user space doesn't exist. Init hasn't started yet.
But at that point, you're talking only about extend. Extend has
No, we're not. We also ask the TPM for a random number, as I said.
Yep.
Okay.
So we use various features of the TPM to do various things.
Okay.
But also you want to try to avoid the case where the TPM is reset between the point where the kernel was booted and measurements were changed.
Yeah, we have to guard them. We're part of a chain that has to guard the measurements that were given to us as well. Now, right at the moment, unless I can get this mechanism into UEFI, that chain is still broken. I can't guard that chain. I can't prevent a reset in the UEFI phase at the moment.
One thing that may be easier to get into UEFI, I don't know, is another mechanism to detect resets is to have early boot / UEFI extend a secret value into a PCR, and in the event log only report the resulting PCR value instead of the extended hash. That way, user space can detect whether it is still in a boot sequence that was started off by the UEFI that you trust, or whether it was reset on in the meantime without you having to do any kind of elliptic curve crypto or session key passing or whatever.
Right, but if UEFI puts a secret value in, how is this secret to anybody who has access to the firmware?
Well, yes, of course.
You
need to bootstrap it at some point.
You need a random number generator to do that, or else you
No,
get a value somewhere.
it's not a random number. It's a secret number.
No, but it has to be random because there's no secrets. The firmware flash is readable.
Yeah, that's the problem. And the things that are snooping the very bus over which the firmware will go.
Okay, one last question for me,
Yep.
James. With regards to TrenchBoot, I like your idea in general, but...
well, that's a change. Nobody usually likes mine. Okay, question.
To some extent.
Thank you.
But the problem is, as I said in my presentation, we need to access the TPM from the early code. And how do you want to put crypto stuff into early boot code in uncompressed kernel?
It's already there. So the proposal for the Linux kernel involved the addition of no crypto code at all. The kernel itself already has code for handling elliptic curve keys and AES encryption, which is all we need, and for hashes, which is all we need to derive the HMACs and do the encryption and decryption of secrets. So the kernel itself had all the code. It was just there was one piece in the elliptic curve cryptography that wasn't working that I had to make work, and there was another. It didn't have the CFB streaming cipher the TPM uses, so I actually added that to the kernel's crypto system. UEFI can do the same thing because secure boot requires exactly the same primitives. In fact, UEFI is more capable because it has OpenSSL sitting in there.
But is it in kernel proper, or is it in kernel, an early uncompressed kernel?
If you're asking, so the crypto system currently is not part of the compressed boots, the uncompressed bit of the compressed
This is a problem for us.
But at that point,
Mike,
we have the EFI
please.
stub. At that point,
sorry.
At that point, we have the EFI stub, though, so we can actually call EFI to do it.
Excuse me?
We can use EFI code to do that.
Yeah.
We don't need the kernel to do it.
Which is what I do. If you look at the way I modified TianoCore, I've extracted the PKCS7 verifier, which is what I use to actually do secure boot in my preloader that has no crypto at all.
So you suggest that we should use UEFI calls to communicate with TPM, and then
use UEFI calls to do crypto because UEFI is the extant thing that's uncompressed that has the crypto libraries.
Okay, what we should do on non-UEFI platforms?
Make them better.
Pray and have them effectively discontinued. Yeah.
This guy has problems with that.
Well, look.
Mike.
Okay, so what we're getting into is a philosophical question of should we have cryptography in the fundamental boot sequence? And the answer is that without cryptography, we can't establish trust with entities whose only trust path is through cryptography. So either you do cryptography or you're happy with an untrusted operating system. These are the only choices before you. So if Coreboot doesn't want to do cryptography, it has to be happy with an untrusted operating system, or happy trusting the fact that it may or may not have been compromised in the boot sequence.
I wonder what Google will say for that.
Well, Google will say that they've already got cryptography in the Titan chip, I would imagine, right? Okay, Google is going to say something.
So not speaking on behalf of Google, but yeah, for production systems, we don't, if we're using Titan, then we don't have TPMs anyway.
Yeah, but Titan is also cryptographically, it's a cryptographic system, but it's self-contained. What we're trying to do here is to emulate a self-contained cryptographic system. And that means that all of the participant components have to be able to do the cryptography we need to do that. Okay, so I'm completely out of time now.
Yeah, we're finished. Thank you, James.
You're welcome.
Now Philip Trika will be presenting reference integrity measurements for TPM2.
Hi, my name's Phil. I've been working a little while now on some of the TPM user space stuff, and I've started kind of branching out as that's gotten stable and kind of self-sustaining. I think this is a particularly timely topic, and we've already had a couple questions about kind of similar stuff in the last couple talks, so hopefully you'll agree with me. If not now, then maybe by the end. So I'm going to make a lot of assumptions, and that seems to be perfectly all right because y'all are asking really good questions, and you probably already know all this stuff anyways. In case anyone's interested in terminology, that's the words, these are the words I will use. Other people may use other ones. Attestation seems to be a particularly hot topic, and everyone seems to kind of be reinventing some of the terminology. So those are the ones I'll talk about, but I don't think I'm going to really have to go through that for this audience. So the important thing, though, is understanding what these entities do. The thing I'm calling the verifier, which is the component of the system, if you're doing remote attestation, that makes a challenge to an attestor and receives attestation evidence. This is going to be a signed manifest of PCR values, the TPM quote that we all know and love, and some supporting evidence that is the event log. The verifier, of course, must first verify before it does anything particularly interesting. It has to trust the information that it's received, and it has to know that the integrity of that information is intact. This is by bootstrapping trust with a signing key in the TPM, things that y'all have already seen before. But verification is definitely a necessary precondition. Alone, it doesn't get you much. This brings up the notion of appraisal. So the verifier receives this information. It establishes that it's both from a trusted source and that the integrity is intact, but it needs to actually inspect this information and figure out what it means. When you're doing remote attestation, if you're not looking at the event log and you're not able to deduce anything useful from it, all you know is you've gotten a quote from someone and that the event log is associated with the information that came out of that TPM. Appraisal is effectively your trust decision. You look at it and you decide whether or not you're willing to do something. Typically, this is an access control decision, but that's not always the case. And so these values, sometimes people will hold them up next to each other. There are systems that will say, your values have changed, therefore I may trust you differently than I used to before. But really, you want something that's, like a whitelist or a blacklist. You don't want to have your trust based on simply previous knowledge of the system. And again, knowledge is really important. It's the verifier has to have sufficient information to make this decision. And that seems to be where we've all fallen down pretty badly with remote attestation. The knowledge of what's in this event log and what that means to the larger system is something that I think we're particularly missing. Now, James was talking previously about some special sauce that IBM has up on SourceForge. That's awesome, but we want this for everybody and all the things. So really, where I want to start is in the software build process. And this is just how things kind of work now, right? You get your source code, you build stuff, you got some configs that may come in with, from your distro packager. It ends up on your attester. This is your laptop or your server or whatever. These things get measured as they're executed, hopefully. They go into the TPM, which is your reporting mechanism. The attester receives a challenge from the verifier, provides the information up to the verifier. The verifier appraises it, hopefully has enough information, but in this diagram, there's really just a box, and then makes some decision. The thing that's missing here, though, is the knowledge of what's in this event log, what these measurements mean. So this brings the topic of a reference integrity measurement, and there were already some discussion here today about the RATS effort in IETF. There's similar work going on in the TCG. My understanding is that they're working together. I hope that's successful. And I'm trying to get into it now, which is pretty interesting. But for the most part, measurement is a fancy way to say hash. It sounds a lot smarter. Maybe that's why we say measurement instead of hash. But the RIM is really just meant to include, at the very least, this hash and some config and metadata. The RIM also can mean RIM with an extra M on the end of it, which is just a manifest. This is a collection of these measurements. It could be one or more. And this effectively becomes like the unit of information in your appraisal corpus. So we update the diagram there to hopefully instrument the build process so that your build artifacts include the identity of the binaries, the config, whatever it is you're creating, and makes that available to everyone, hopefully. And this allows the verifier to kind of consume this through some mechanism, not saying exactly what, but this is the information that becomes your appraisal corpus. So I did a bit of a proof of concept with Grub2 just to ground this in some reality and to prove to myself that, that this can actually be done. The idea here is to generate some kind of RIM with some information, not saying we're covering the entirety of Grub yet, but hopefully as much as we can. And so this is really just calculating the identities of these Grub2 components as we're building them. This is independent of the event log. These are just, we're not looking at the event log to get this information. We're not replaying it and just pulling it out of the event log after the fact. We want to do this as part of the build process. So the next step is to obviously, once I do this calculation, to prove to myself that they're actually correct, which does require getting the event log. So I'm kind of doing a bootleg version of attestation where I'm doing this all in QEMU with emulation, and I just look at the event log to make sure it actually matches what I expect these values to be. And really, this is about motivating future work. I don't want this to be something that's specific to Grub. This should be all the things. Everything that gets installed on my Linux systems, I'd like to get a RIM for every one of the things that lands on that. This includes firmware all the way up. But Grub is a really good example because it kind of fits in nicely and it's close enough to UEFI that can still get the event log without having to have the latest bleeding edge kernel to pull it out. So to bootstrap this stuff, I started begging, stealing, and borrowing from a bunch of the TPM user space stuff that we've been doing, pulling a test script from some of the UEFI integration that I've done. This is the only reason it was possible. Software TPM, QEMU, OVMF, excellent stuff. Makes it so you don't need separate hardware to actually do this testing. It's brilliant. Ported an example code or a bunch of example code from this UEFI stuff as well, so that in the Grub shell I could just dump the event log and capture it nice and easy. This is in a branch that I've got up on GitHub now. It's very, very simple. It's incomplete, but if there is any interest in kind of moving tools like this into Grub, I'm definitely open to the possibility. And of course, we've got to be able to calculate the identity, aka a hash, of these components. This is a wonderfully drowned out color code there. But this is meant to be a sequence diagram showing the interaction between, or really the events that are happening as Grub is coming up and processing. So this is literally, if you were to look at the event log, you would be seeing these events as they're recorded. So firmware stuff happens in the beginning. We'll kind of ignore that. But the firmware kicks off Grub through the boot x64 EFI executable. And of course, the UEFI will measure this before it executes it. So the measurement goes into the TPM, and it records the event in the event log. And then we see this kind of happen ad nauseum. This is just how the measurement process works. Grub itself comes up, loads the normal module. Then you see all the processing for the dependencies. These end up measured, recorded in the event log. Measured again, recorded in the event log. And that's this kind of this loop down here. And finally then, Grub hands off to something else. Whatever, your Grub config might be that thing. I'm a little scared of Grub config, so really I just had this thing drop straight to the the shell after that point. And it was sufficient, at least for the example. So this is a snapshot of an event that's coming out of the event log as dumped by the grub shell. So the test for this is just running OVMF in QEMU with a software TPM backing it up. And so the event numbers at the top there are the 33. This was the 33rd event. The type there is actually from the EFI application measurement. So that's the type that you'll see when EFI kicks off an EFI application, either from the EFI shell, or in this case, we're using you can see the name down here, bootx64.efi with a space in between each one because wide characters. But the thing that we care about here is the SHA-256. That's it right there. And it turns out if you were to just run bootx64.efi through SHA-256 sum, you will not get the right answer. For whatever reason, UEFI does some stuff where it only measures parts of the executable. I'm sure there's a reason there, but I don't know what it is. I'm sorry?
It's the loaded segments. It's not the ones that aren't marked as loaded in the segments. Just don't get that.
Well, there you go. Like I said, I'm sure there's a reason. That guy over there knows it. Thanks, Peter. But what I did was actually steal a bunch of code borrow a bunch of code from the Secure Boot signing tool. And that had all the knowledge needed. All I had to do was, instead of having it spit out a PKCS7 structure at the end, I just lopped all that code off and just had it print out the hash that it calculates. And you can see there it is. That's the identity. We've got the first grub executable measurement pre-calculated. Also, just an example showing that loop previously, the module that I wrote that drops into grub to show this stuff in the grub shell is called tpm-cmd.mod. And so in order to actually dump out the event log, I had to manually load that insmod in the grub shell to have it pop up. And it shows up in his event just like all the other modules. And you can see through the event log, this is event 48. Grub was loaded, it was the 33rd. There were however many events in between that were a bunch of modules being loaded and whatever else grub was doing. But for one specific module, we'll grab the SHA-256 sum. This time it is just a nice simple SHA hash. Thank you, grub, for doing simple things. So as far as integration into a build system goes, that's a lot easier. But UEFI wasn't impossible. So the output from the proof of concept hopefully is a discussion about what all this means and how we integrate this into the larger ecosystem. For grub, it's possible. I've ignored a lot of stuff, but the worst case in this so far is not an unsolvable problem. Worst case was UEFI PEs here, and Peter will help us figure out all the ins and outs there. I had to cannibalize some stuff. It's not really a sustainable way to do it, but it can be done in a reasonable way, I'm sure.
I already have, just not in that package, in the other one.
Right, so there's, all this code is in the UEFI, like in EDK2, right? EDK2 has the code that loads this stuff up, it does the hashing. The problem is that it's buried really deep in there. And I've heard there maybe more than one instance hiding in the source code too. So that would have been a lot of spelunking that I just kind of sidestepped. Obviously more questions than answers. Really, we want to know how deep this appraisal process can go. So for grub and maybe some closed source stuff, this can get us a link back to a binary, and a binary that comes from a source that we may or may not trust. Marrying something like this with reproducible builds so that we could actually delve down all the way to source level kind of transparency, I think that's really the ultimate end goal. The end goal should be that I can look at my event log, I can get this RIM that came from whoever produced that, I can verify that it's the same thing, and if I really want to, I can grab the right version of the source code, build it, and get the output with the exact same hash. This is just tooling though, right? So you need tools to generate RIMs in the right formats, we got to do all this hashing. The formats are still something that's under discussion. Most of that's kind of at the information model layer, so it's not even really a concrete format right now. So there may be some opportunity to influence that as well. And of course, the last bullet here is probably one of the harder problems is how do we go about distributing all this stuff? How do we communicate this from our build infrastructure at like kind of the distro level out to all the end consumers? Still an open question. It's a big infrastructure problem, I think, and could be an interesting one to take a crack at. That's it. So, anyone who wants to chat about this stuff on, at any scale, I think Grub's probably a pretty good first place to start integrating this stuff. It's kind of at the lowest level that we can access without having to go through the UEFI forum, which is a little scary.
I have a question. What kind of problems do you have with Grub CFG?
It's complicated. That's really all it is. Right now, if you look at the event log after Grub has processed the config file, you'll see an event for every single thing that came out of the config file. That's not bad, right? It's thorough. It's very thorough. And it's going to give you a lot of RIMs, right? You have to have one reference integrity measurement for each one of those steps in the config file. If you automate it, it's probably tractable, but it brings up the question of how many paths are there through. Yeah, so I got the hashes on this working on the plane right out here. So the config file was, future work.
So just to comment on the hashes, I'm sure the two signing tools, SB-Sign and PE-Sign, will be happy to output the hashes. The only reason we didn't is because we didn't think anybody had a use for them.
Oh yeah, completely. I didn't mean to,
James,
I wasn't
wrong.
casting.
I did do it.
What, sorry?
PE sign dash capital H.
Okay, I don't use PE-Sign, I only use SB-Sign.
Yeah, again, that was the only one that I had. I didn't go as deep as I could have there, and I didn't mean to cast dispersions in any way there. This is just to get the information I did what I did may not have been the easiest route, and I'd be happy to find an easier path.
Sorry, just going back to your question a moment, one of the other problems with grub config is variable expansion.
Yeah, so pre-calculation with variable expansion sounds tough.
So one of the discussions that I had on OSFC was maybe use LVFS for providing some PCRs value. And Richard was already able to get from vendors PCR0.
Oh, right. So the FWAPD and all that stuff has some of this. It's, there's always more to do though, right?
Yeah, but he started and he's like probably the best place and the most results right now. So if there will be some ecosystem which can integrate with LVFS and provide more measurements,
definitely,
that would be cool.
I agree completely.
Did you try anything with TXT or other SRTM related?
Sorry, one more time?
Did you try Intel TXT or any hardware rooted trust?
In a past life, I've done some stuff with TXT and with calculating PCR 17, 18, and 19 values. It's possible. I've got some reference code, but it's kind of unrelated.
Okay, not as in grub is what I was.
No, not at all. not for this.
Any questions?
Great. Thank you.
We are finished. Thank you. Now there will be two talks made by Piotr Król. One non-UEFI error measured boot using core boot. And the next one will be TPM to the 0 Linux sysfs interface.
Works? Proszę? I can start with UEFI, no problem. Like I'm not sure about the maybe. Okay, sure. So yeah, I will bore you for next 40 minutes. So because I have two presentations. So maybe this is really more interesting. So maybe, can we start? Or?
Yeah, sure.
So I will talk about Non-UEFI, our measured boot, using core boot, grab, and TPM, or whatever else you will propose. My name is Piotr Król. I'm founder and embedded system consultant at 3MDEP, Poland-based company. I'm from open source firmware ecosystem. So boot process right now its integrity is dominated by UEFI compliant systems, but there are some firmware providers or platforms with firmware that care about something different. So we have core boot, LibreBoot. There is ORBoot, which is Rust implementation of core boot. There is UBoot, there is Linux boot. CBIOS, important on some probably cloud environments. And there is also still the GASE BIOS and UEFI or UEFI CSM, which we still have. There is also SkiBoot, but I believe this problem was already solved in a different way. So existing solution that I'm aware of are Petit Boot, which doing measured kexec to Linux, or not doing yet, but can do because everything is there. And there is Trusted Grab, which use a TCG extension interrupt 1A, which I will talk a little bit later. But it requires someone to install that interrupt before. And there is some effort from BSD world, Hardened BSD call for participation. There is an effort because BSD systems also boot on non-UEFI compliant systems, so they care also about that. So who should care? Yeah, Chromebooks, I believe. If the users want to repurpose the devices, then they use CBIOS, and then maybe if they would like to have measured boot, they need that. Of course, users of previously mentioned firmware stacks, all distros with legacy boot, and maybe some cloud providers where CBIOS in QEMU is used. So what we really need. So we have this static core root of trust for measurement, and we execute measure, extend PCR, and execute some phase. So this is, and in here we have non-UEFI compliant firmware. We do the same. We're going to bootloader and doing the same to us. And what we really need to make this chain work for all systems, not only UEFI. So who can care, like Linux, BSD, L4-based OSs, and others. So what's the state right now? So in coreboot, we have this measure, extend, execute chain with vboot. But finally, we load some payload, which is already measured. And from that payload, we have to do something. Sometimes it is CBIOS, and CBIOS install this TCG extension, but then have to jump to something that will use that. And most of the systems simply do not implement that. Linux boot seems to have different approach. They probably will use something similar to Petit boot, so there will be measured kexec, but it's not there yet. Yeah.
I just make an observation, which is that the measure, extend, boot isn't quite enough. We need measure, extend, log, and then boot, so we can actually verify the log.
Yeah, sorry. And so this is assumption that if we're doing this, we also logging.
Okay, but where the log is and how we get to it is the nastiest bit of all of this. It's what causes
I believe it is standardized. So we have this ACPI space where we, this reserved area where we put this information. So Philip probably used that during the implementation.
Okay, as long as we can get it, it's fine.
So for TPM2, the implementation of the log is very UEFI specific, but there's some patches in the core root universe, CBIOS is repurposing the TPM 1.2 ACPI table to provide a link to a TCG2 event log.
Yes, we're already using that, but my problem is that this chain ends at CBIOS.
Sorry, answer James in terms of ending stuff up.
Okay. So we're thinking about it. We have a potential solution. That's my answer. Okay.
So in case of grab as a bootloader, it depends how and what we boot. So it is possible to put grab into core boot as a payload. So in that way, it's verified during the firmware verification phase. But still, then from grep, we have to jump to something. And if we have a kind of legacy system which rely on MBR, then there is no support for, because grep will not install this interrupt handler, and there is no other way. So grep other way could also do kexec. So CBIOS provide that interface, as I said, and Trusted grep 2 use that. I'm not sure why Trusted grep 2, like it's different implementation, and I'm not sure how, if it is possible to take those changes and somehow port that to grep.
So the issue there is that the code that was in Trusted grep 2 derives from code that was in Trusted grep, which was written by a Japanese research group that I haven't been able to get in contact with, and which I'm not sure currently exists. So there's no way to do the copyright assignment to the FSF.
Okay.
So it needs to be rewritten, basically.
Okay.
Unless someone can find the people who wrote it in the first place and get them to sign paperwork.
Or we relax copyright assignment for the grub project, which is not impossible.
Okay. So other problem with Trusted grep 2 is it only supports right now 1.2. It does not support 2.0. So, and there's like long thread about that. Yeah, so exactly. So Trusted grep using this TCGPC client specific implementation for conventional BIOS. And yeah, so it supports only 1.2, but this, I believe this specification is not only about 1.2, but is in general. So it can be, it can match also 1.2 and 2.0. And to just define, to quote the specification about this interrupt, it allows the caller of the interface to have direct access to a limited set of TSS functions and pass through to the TPM. Of course, these functions are installed by some previous stage. Yeah, so there is cool discussion. Matthew's there. Various other people are there on this issue on GitHub. Yeah, so maybe this is like more discussion stuff than really proposal, because I believe that I see only two solutions for my problem. So first of all, I don't have any code or any documentation how Petit boot managed to perform measured kexec, or even maybe it's not there yet, but what would be the plan? And second, I believe this yeah? That's great.
So you're correct to say that Petit boot doesn't do this yet. What it will do is use the kexec file load syscall. So currently just uses blind kexec. That will then go through IMA, the integrity and measurement architecture, and that will do your measurement and also the verification, if I've understood it correctly. Otherwise, some of my colleagues are going to yell at me when I get back.
Yeah, that's the answer to my question.
Yeah, that syscall verifies that whatever you're loading next is signed and trusted, and yeah.
So I believe the same way Linux boot should implement that, and I know those guys, so probably we'll try to kind of align this effort, because it doesn't make sense to have many other implementations. So my question are, is there any other solution that I'm missing for legacy non-UEFI our systems? Does it make sense to still implement this old 2012 stuff or int 1A? Yeah, and can we really kexec everything? And for example, how happy BSD systems will be with that?
So in terms of I don't think there's any other obvious solutions you're missing. So in terms of does using the int 1A thing make sense, I think there's a couple of ways of looking at it. First is obviously that's x86 specific. And there are other platforms with TPMs that would potentially want measured boot.
Yeah, good point.
So that's an issue.
Yeah.
But you've basically got two choices for, say, so if we assume you're using grep 2, then you've got a couple of choices. You can either use the firmware's support for talking to the TPM, or you can talk to the TPM directly. And those are basically the only two options you have. If the firmware has support for using the TPM, well, if the firmware doesn't have support for using the TPM, then you probably never got grub measured in the first place.
Or
Unless,
I write on my own firmware.
Or except in the case where it's core boot has measured grub and then you've jumped into grub. So in that scenario, you would need to be able to write basically a TPM2 driver for grub, and that's then a fair amount of code, and you would need to deal with it being connected to either LPC or SPI. And in TPM2 cases, you need to deal with it either being, there are two different interfaces that the TPM2 can be. There are two different programming interfaces that a TPM2 can expose. So you need to be able to handle both of those. So I'm not saying don't do that.
So then how, even if I will do that, and this will fit into SPI still, how I will continue? Like what's, like, okay, I have TPM support in grub, okay, then I can continue because I have this.
So the other problem is that if the firmware previously was generating an event log, you're going to need, if you're doing this yourself rather than using firmware calls, you're going to need to be able to find the event log. You're going to need to be able to extend the event log, and then you're going to need to ensure that you're still correctly passing on the event log to the next stage.
Yeah, that's, and the question is if kernel will support that, like if Linux kernel will.
The kernel should be absolutely fine with that as long as you expose it via either the way that CBIOS is doing it or the way that legacy BIOS.
So CBIOS doing it correctly through API.
So there is no spec format for doing TPM. The Trusted Computing Group did not spec a format for doing this on non-UEFI systems. So when we say correctly, the kernel supports the way that CBIOS does it, and so that's basically the de facto standard that you could work to. Or rather, the kernel will support the way CBIOS does it. It doesn't currently.
So that's TCG group, does TCG say explicitly that this is only specification for UEFI hour systems?
The PC client specification for TPM2 only covers UEFI systems.
Okay. That's very fair.
So I would say if you're in a situation where you can use CBIOS, then yeah, use the int1a interface. If you're in a situation where you want to support this without necessarily having firmware that supports it yourself, you're pretty much left with having to implement raw TPM supporting grub.
Okay, what about kexec and is kexec, so you are in the camp of int1a?
So the alternative is, if your payload is Linux, if there's no intermediate, then Linux knows how to drive the TPM. So then you can have kexec. Kexec with IMA should do this correctly and should pass the log on to the next thing. So yeah.
Okay. In theory.
Any other questions?
Maybe just a comment. I wouldn't totally rule out that the TCG might come up with platform-specific profiles beyond UEFI x86. So you might want to, I don't know, consider having your company somehow collaborate.
Yeah, we are TCG. UEFI adopters, but that means nothing. Yeah.
With TCG, because otherwise you implement one thing, they at the same time come up with a different spec, and all of a sudden we have two competing standards once more, an industry standard and
I kind of see that kexec starting to be de facto standard, especially that IBM pushing that hard. So, and probably Linux boot will push that hard, so we will have Google, Facebook, and IBM doing kexec.
I'm mostly talking about earlier in boot, like, I don't know, U-boot-based platforms, ARM, whatever.
Yeah.
The kexec root of trust, I think that there is a kind of a risk, and it was mentioned briefly on the list, that it's not, you don't get quite the same guarantee as when you boot up in terms of having the chain of trust starting with the hardware, and that if there was some sort of DRTM type solution where you can actually re-establish the new kernel and somehow tie that to hardware, you would be in a much better state, because the current running kernel, if it's long-lived, may have been compromised and may be feeding.
Yeah, so in case of the RTM, we are behind AMD effort for TrenchBoot, so we are aware of the RTM possibilities and definitely working on that, but still, I hope to solve that earlier than the RTM will be in upstream Linux, upstream grub, and so on, because this seems to be much longer way.
we can't do DRTM without a TXT transition, and you can't do a TXT transition without an external attestation server. We can't require an external attestation server for boot, so we can't do it.
I'm doing AMD, and there is no binary blobs there, and implementation of secure loader is open.
What external entity verifies your static measured values to allow you to transition to the dynamic?
So as you said, IBM got this implementation of attestation
We have
server.
an external attestation server. You can't condition boot depending on an external attestation server unless you're a cloud provider doing everything, which we are, but it certainly won't work for laptops.
Yeah, that's a good question. Like, definitely I'm looking for some, but this is completely different discussion. This is not on the topic. We're looking at the remote attestation for all platforms, not also embedded systems. So, and I hope that this AMD-based implementation will be kind of role model since it's working already.
I'm not saying dynamic is wrong. I'm just saying transition from static to dynamic requires an external entity to verify, and there are certain situations where you can't get that entity.
Yeah, James, wait. As I remember, the DRTM idea is that you don't need to trust anything which is in the gap, let's say. So everything, the trust for dynamic root of trust is rooted in the hardware.
That's the idea, but the reality is
yeah.
We have
I know what you mean.
SMIs and we have ACPI. And for SMIs, we have SMI transfer monitor, which is already merged to, like they're working on merging that to core boot. The NSA working on that. And for ACPI, you can measure that. So you can verify that in secure loader. So yeah, but I agree, like definitely those two things should be connected. And I believe like work of IBM can be leveraged to use that in different environments, not only in the server environment.
So it definitely can if you want to, but it still depends on an external attestation server.
Yeah, I agree. I agree. I do not disagree that statement. Okay, I have some marketing here. on next slide. Can I move on?
Yeah.
So, not yet. Summary. Okay. Okay. So yeah, this is like the FreeBSD guys also expressed their opinion on the forum. Like it was like completely no. It's like stupid idea. Okay, executing FreeBSD.
I think that you should ask James.
This was 3 years ago, so maybe things changed a lot. Yeah.
So there are definitely CSMs that have int1A support. There was a period where basically systems were being sold that were UEFI based, but which never exposed UEFI and were just using the CSM. And many of those did have trusted boot support. So there are implementations out there in the proprietary world. Whether there are free software implementations, I'm less sure about.
Yeah, thanks for that.
I think that you should ask James about marketing stuff because
no. I'm sorry. This is like it's on other presentation because you switched them. Like I thought the other one will be first. So I just wanted to tell that there is Platform Security Summit at the beginning of October in Redmond, and there will be a bunch of interesting people doing stuff related with security from various companies and communities.
On PowerPC machines, you basically don't get a choice about being K-exect. That's the way we boot things. So I think FreeBSD has come around a little bit since 3 years ago, at least for open power machines, because otherwise they can't boot.
Okay. Thanks for that comment.
So, I don't know, check.
Any other questions? Thank you.
Shall I move on?
Yeah, go ahead.
Okay, so I have other issue here. So yeah, TPM 1.2 is not compatible with 2.0, and yeah, there was this long thread on Linux integrity mailing list about sysfs support for 2.0. So unfortunately, not developers and user space people know that TPM 1.2 is different than 2.0, completely different. Yeah, and there are some tools, scripts, some user space stuff that just assume some things about sysfs and checking things in sysfs. And there are some TPMs that are capable to be upgraded to 2.0 just by firmware upgrade. And to be honest, those also can be downgraded. So you can switch version of TPM that you have to some extent. The number of upgrades is typically limited. Yeah, so you can have some models that work as one or another. And TPM2 software like moves very fast, and like most of the distros are not up to date. Yeah, so this is like excerpt from Core OS documentation. Almost any other non-zero, non-error output from reading the IDE file indicates that supports version 1.2. So yeah, so this is kind of like sounds like a vague way of detecting what we're playing with. So my problem is like we have no common way of identifying if we're playing with 1.2 or 2.0. And yeah?
IBM has this problem as well. We're interested in actually adding to sysfs just a variable that tells you what the version of the TPM is. I take it that would satisfy your use case as well.
Yeah, I started this thread on Linux integrity and get various proposals. And yeah, probably we can say this is already answered, but I want to just present that to what was the reasoning and what kind of proposals we have from community.
The latest kernels do expose what TPM version you have in sysfs.
But is it consistent for board version?
Yeah, it shows it in dev firmware node description. It's either a TPM 1.2 device or 2.0 device. It's there in sysfs.
Firmware node description of
firmware
ACPI or
sys class TPM, TPM 0, whatever device firmware node description.
I don't think I've got that.
Yeah, we should probably check code right now. Yeah, so this is the same. This file is also exposed for both, yeah?
Yes.
Okay. So maybe I should stop talking.
No, that only goes to the ACPI description. It doesn't tell me the version.
So this
as I've said before, I think it's sustainable to have a file that tells the protocol version, given that for some backends you need the probe message, and for some backends you can get away without the probe message. For example, if the ACPI tables tell that. So it doesn't really do harm, and I think it would be nice for the daemons that they can kind of configure themselves for the right protocol before trying to do any TPM communication. So I can align with that sysfs file.
Well, I would say this is useful even for things like our user space resource manager. Right now, it just jumps up and talks to dev TPM 0. If it's a TPM 1.2, it just falls down.
Yeah, and let me add that for me it would be useful even just for like when I enable like new, like let's say Intel hardware platforms, just as a smoke test that there's something going on, that TPM is detected, you know.
Yeah.
So we looked at the firmware node description. My laptop has it. His laptop doesn't.
Okay.
So we still have a
Yeah. I think when we exchanged like a few messages, even then I said that file is, you know, set the patch and I will review it and
we'll send the support review it.
Sure.
So just for complete clarity there, the firmware node description literally just presents a string that's in the system ACPI tables. So that's something that's completely outside the kernel's control.
Right.
So it doesn't exist on this laptop.
But even if it always would require that probe message, it still would be like quite nice, convenient feature to have.
Yeah. So there was quite long thread.
But I think like having like files for getting all the PCRs, that would be just kind of. I would say that it's even kind of that kind of it can be even considered something that some administrator could consider as an information leak. So it's better to keep it under control, so that you get that information through the dev TPM. But protocol version, that can be public.
I mean, we can't consider the PCR values to be an information leak because they're an unprotected asset of the TPM. Anybody can get to them. So they can't leak information. The question is whether, I mean, we can't display them in sysfs in the same way as we did for 1.2 because it violates the one value per file rule. So if we want to do it, it has to be a two-level subdirectory that goes by bank and PCR number. But we could do it if we wanted to. I'm just not sure we want to. I'll leave that to other discussions.
Well, what do you think about the because I mean with TPM 1.2 it also publishes the public part of the endorsement key, because it kind of it's an identity to the machine, so it can be considered from some perspective as an information leak.
Right, I don't disagree with that. Oh, sorry.
I was just going to say, I think we can definitely argue that the TPM 1.2 sysfs layer was not well thought out.
I think for actually it would be nice to have patch for TPM 1.2 that would, let's say, a boot parameter that you could use to kind of disable some of the sysfs files, like the one that exposes the endorsement key public part.
And with TPM 2.0, it usually boots with no endorsement key because it has the seed, but nobody's derived a key from it often. So we have nothing to display unless we want to derive the key, which means we're prescribing the encryption system and everything else, which we don't want to do. Yeah, I think we're done.
Okay.
At least I believe this is very good topic for Linux plumbers because, you know, like all this discussion, there is traction here. So yeah, I just wanted to prove something here, but you know, you already agree with me, so I don't know if I should continue. So this is statistics from GitHub, just showing.
Question.
Oh, excuse me.
Somebody mentioned that exposing the public endorsement key is problematic.
It's an information. Someone can get access to it. They can trace it directly to your laptop. It's unique identifier.
Okay.
So we did some scanning of GitHub stuff, and you see that like most people using cancel in user space, but owned caps enable PCRs are not so useful for people, at least. So I see in Google Code, in CoreOS, the Linux test project, there's some even FWPD stuff. There are a bunch of projects that, so CubesOS, of course. Yeah, so there are a bunch of projects that use that and assume that the structure in sysfs is as it is. And then if you will change something, these tools will probably break and just throw you an error, and who knows what will happen. Yeah. Probably someone never tried that with different version of TPM. Yeah, there is description for that. So I believe this documentation should be improved or changed, or I don't know, like, because it's not say like it's TP 1.2 specific. There were some tries and some patches and some discussion, and this topic are coming back a couple times. Yeah, so I'm not sure. Yeah, so maybe just. Yeah, I'm not sure why this is not displaying correctly. What's going on here? Yeah, there were a couple proposals for that. Some people said like completely no way. There's no way to exposing that. Some people said there are various names of files, like we should have version file or protocol major. This was from Jarko. There were also ideas like you should write C code and query dev TPM, and yeah, I believe like there should be patch like RFC for patch with just sysfs TPM version, and we will see what people will say. Probably this would be fine. Yeah, there was also idea about security FS. So those are the ideas that people proposed, and I believe like the file which saying version is fine. I wanted to show you also, apparently it's not rendering correctly, I'm not sure, it's probably PDF stuff, I converted that to PDF. But you can just list the files that you see for TPM 2.0 and 1.2 and see how big is the difference. And like user space relying on those components and will break simply if those are not supported. So the question, what we're doing in case of other things like cancel, I don't know how cancel is used, but it's used very often in user space. So I understand that PCRs rather not for TPM2. I understand that version is the way of solving this differentiation between the things. But what about the other sysfs files which are not existent for 2.0?
So some of them, stuff like enable, owned, and so on, just don't apply to TPM2 in the same way.
Yeah.
The model's completely different, so some of them sort of vanish that way.
Yeah, so we're relying that somehow when user space tools do that, they should simply first query the version file and apply correct method.
Right. There's no way that we could expose information there that would allow them to do anything useful. So exposing them in the not exposing them in the first place and letting the tooling break is arguably the right thing to do.
Mm-hmm.
But yeah, having a clean way for it to handle that case rather than trying to open, oh, it doesn't exist, this must be a TPM2, is suboptimal.
Yeah. Yeah, and I already told you about the conference, so I believe I'm done with this topic. I probably will try to create some patches to send that version stuff, and I don't know, user space just have to align over time. But like this notion that on mailing list there was this discussion that like we don't care that it breaks things, or we don't care that this is a completely different thing, and we don't care about keeping compatibility or giving like a common mechanism. You just should implement something in C or do something complicated to identify. It's like, I believe it was incorrect.
So I think the main issue is that there's not much you can usefully do with a TPM without having to write C, or some other way of accessing it. So arguably,
you have tools. Like
yeah,
tools.
So with TPM 1.2, there was some relevant information, like the own state, the enabled state, and so on. That's information that you might want to read out in order to then make a conclusion about which of the ACPI physical presence methods you want to call in order to turn the TPM on. And that could be done entirely in shell. But with TPM2, that's not really as true. In order to know that you need to reset the TPM, you really need to be doing some stuff in C first. Well, some stuff via the device node first.
Yeah, but for example, for cancel file, what was the usage for that and why it is used so frequently?
I have no idea.
Anyone?
Sorry, what was the question?
Cancel file in sysfs.
I can only imagine that people included it for completeness because it just was there.
But it's the most used, sysfs file.
So yeah, as I said, people have, I believe, have included it because it was there and easily accessible. Because in practice, even if you call cancel on a TPM operation, if the operation has already proceeded too far, the TPM will still keep on and continue. So the TPM will tell you either RC canceled, yes I canceled, or just RC success, I succeeded anyways. And the only operation that actually takes long enough that I can think of that might justify a cancel is RSA key generation, and a lot of people are switching over to ECC now, so there's not much left that you actually want to cancel in practice.
Okay, thank you very much. That's all from me.
So that's all for today. Thank you for coming. Thank you, Matthew, for taking notes, and Joel for helping leading the conference, and thank you for all speakers. And see you next year, I hope.